Welcome to the Late Lab. It's great to have you here. Before we begin, where are you watching from tonight? Maybe you're lying in bed winding down, sitting somewhere quiet after a long day, or just putting this on while you relax for a bit. Wherever you are, hopefully you're comfortable and ready to spend a little time exploring something strange and fascinating. If you enjoy these slower, thoughtful dives into science, and you'd like to see more of them, leaving a like and subscribing really helps this small channel keep going. And if you're already subscribed and coming back for another late night visit, thank you. That support really does mean a lot. Now, tonight's topic is one of the strangest ideas modern physics has ever uncovered. It's not about massive explosions or distant galaxies, but something much quieter and far more puzzling. A discovery suggesting that two tiny particles can remain connected, even when they are separated by enormous distances. So if this ends up keeping your mind turning a little longer than you expected tonight, at least you'll come away with a better understanding of one of the most mysterious phenomena in physics. So let's begin. What exactly is quantum entanglement, and how did scientists discover that two particles might remain linked across the universe? For centuries, the universe appeared to follow rules that felt reassuringly predictable. Objects moved because forces pushed or pulled them. Planets followed graceful paths through space. Light travelled as waves through empty space. The framework built by Isaac Newton and later expanded by James Clerk Maxwell seemed powerful enough to explain almost everything scientists could observe. Newton's laws of motion described how objects accelerate when forces act upon them. His law of universal gravitation explained why apples fall toward the ground and why the moon circles the Earth. Maxwell's equations united electricity and magnetism into a single theory, revealing that light itself is an electromagnetic wave moving through space at an enormous speed. By the end of the 19th century, many physicists believed the fundamental laws of nature had essentially been discovered. In fact, some scientists even suggested that physics was nearly finished. That belief did not last very long. When researchers began probing the smallest scales of matter, particularly inside atoms and within the behaviour of light, strange inconsistencies began to appear. The classical laws that work so beautifully for planets and falling objects began to falter when applied to the microscopic world. One of the earliest warning signs came from a problem involving heat and light known as blackbody radiation. A blackbody is an ideal object that absorbs all incoming light and then re-emits energy as radiation depending on its temperature. Physicists in the 19th century attempted to calculate how much energy such an object should emit at different wavelengths. The mathematics seemed straightforward at first. Classical physics predicted that as the wavelength of light became shorter and shorter, the energy emitted should grow larger and larger without limit. According to those calculations, a hot object should release an infinite amount of energy in the ultraviolet region of the spectrum. Nature, quite sensibly, refused to cooperate. Real experiments showed something entirely different. The energy emitted by heated objects rose to a peak and then fell away at shorter wavelengths. Instead of exploding toward infinity, the curve simply bent downward. This mismatch between theory and experiment became known as the ultraviolet catastrophe. The catastrophe was not that the universe behaved strangely. The catastrophe was that the equations of classical physics were wrong. Around the same time, scientists studying atoms encountered another puzzle. When gases were heated, they emitted light at very specific colours rather than a continuous rainbow. These patterns, known as atomic spectra, appeared as narrow lines of colour unique to each element. Hydrogen produced one set of lines, helium produced another, and sodium produced yet another. No one could explain why. If atoms were miniature solar systems with electrons orbiting a nucleus, as early models suggested, the emitted light should have formed a continuous range of colours. Instead, atoms behaved as if they were only allowed to emit energy in certain precise amounts. Something fundamental was missing. At the beginning of the 20th century, a German physicist named Max Planck proposed a radical solution while studying the blackbody radiation problem. Instead of assuming that energy could vary smoothly and continuously, Planck suggested that energy might be exchanged in tiny discrete packets. He called these packets quanta. Planck initially treated the idea as a mathematical trick rather than a deep statement about nature. Yet when he applied this assumption, the equations suddenly matched the experimental data perfectly. The radiation curve behaved exactly as real measurements predicted. Energy, it seemed, might not flow smoothly after all. Instead, it could come in tiny, indivisible steps. A few years later, Albert Einstein took the idea even further. In 1905, while investigating the photoelectric effect, Einstein proposed that light itself might behave as if it were made of particles. When light strikes a metal surface, it can knock electrons free from the material. Classical wave theory predicted that brighter light should always release more energetic electrons. Experiments showed something different. Only light above a certain frequency could eject electrons at all, regardless of brightness. Einstein explained this by suggesting that light arrives in discrete energy packets, later called photons. Each photon carries energy proportional to its frequency. This idea sounded outrageous at the time. Light had long been understood as a wave. Suggesting that it could also behave like a particle challenged centuries of thinking about the nature of light. Yet Einstein's explanation worked perfectly. Around the same period, other physicists were quietly building pieces of what would eventually become quantum theory. Walter Nernst explored thermodynamic ideas that hinted at deeper atomic structure. Arnold Sommerfeld extended the atomic model developed by Niels Bohr, introducing elliptical electron orbits and subtle corrections that improved predictions of spectral lines. Each of these contributions pointed toward the same conclusion. Nature at very small scales did not behave in the smooth, predictable way classical physics expected. During the 1920s, a new generation of physicists began constructing an entirely different framework for describing the microscopic world. Werner Heisenberg developed a mathematical approach known as matrix mechanics, while Erwin Schrödinger introduced wave mechanics, a method that described particles using wave functions that evolve through time. These new theories agreed with experimental results in astonishing detail, but they came with deeply unsettling implications. In the emerging quantum picture, particles did not always possess definite positions or velocities until they were measured. Instead, they existed in a range of possibilities described by probability. A particle could be here, or there, or somewhere in between until an observation forced the system into a single outcome. This strange condition became known as superposition. Niels Bohr helped develop an interpretation of these ideas that would later be known as the Copenhagen interpretation. According to this view, quantum systems are fundamentally described by probabilities, and measurement plays a central role in determining physical outcomes. Not everyone found this comforting. Albert Einstein famously resisted the idea that nature might be governed by chance. He once remarked that he could not believe the universe plays dice, yet experiments continued to confirm the predictions of quantum theory again and again. As physicists explored the mathematics further, an even stranger possibility emerged. When two particles interact and then move apart, their quantum descriptions can remain linked. Instead of behaving as two separate objects, the pair may share a single combined state. In such cases, measuring one particle immediately determines the properties of the other, even if the two are separated by enormous distances. Imagine two particles created together in a way that ensures their spins must always be opposite. If one particle is measured and found to spin upward, the other must spin downward. But according to quantum mechanics, neither particle has a definite spin until the measurement occurs. Before the observation, both possibilities exist simultaneously. Only when one particle is measured does the system choose an outcome, instantly determining the state of the other particle as well. This phenomenon would later be called quantum entanglement. At first glance, the idea seems almost impossible. How could two objects remain connected when separated by vast distances? How could a measurement performed here instantly determine something happening far away? Yet the mathematics of quantum mechanics insisted that such correlations must exist. For many years, entanglement remained mostly a theoretical curiosity buried within the equations of quantum physics. Even the scientists who discovered it were unsure whether it represented a genuine feature of nature or simply a limitation of the theory. But over time, experiments would reveal that this strange connection between distant particles is not just mathematical imagination, it is real. And it suggests that the universe may be far more deeply interconnected than our everyday experience would ever lead us to believe. Once the early cracks in classical physics had appeared, the next challenge was not simply to patch the existing theory, but to replace it with something entirely new. The strange behaviour seen in atoms and light was not a small adjustment to familiar ideas. It demanded a completely different way of describing how nature works at the smallest scales. During the 1920s, a remarkable group of young physicists began building what would eventually become modern quantum mechanics. Many of them were in their 20s, Several were working in Europe, moving between universities in Germany, Denmark, Austria, and Switzerland. Their ideas would transform physics so thoroughly that even the people developing them sometimes struggled to understand what their equations were truly saying about reality. One of the first major breakthroughs came from Werner Heisenberg in 1925. Heisenberg was attempting to solve a problem that had frustrated physicists studying atomic spectra. The classical picture of electrons orbiting a nucleus like miniature planets simply did not explain the precise spectral lines emitted by atoms. Instead of trying to visualize the motion of electrons directly, Heisenberg took a bold step. He decided to focus only on quantities that experiments could actually measure. Rather than describing electron paths, he described transitions between energy states. To do this, Heisenberg developed a mathematical framework built from arrays of numbers that represented observable quantities. These arrays followed unusual multiplication rules that differed from ordinary arithmetic. Later, the mathematician Max Born and the physicist Pascal Jordan recognized that Heisenberg's arrays were actually a mathematical structure known as matrices. The resulting theory became known as matrix mechanics. Matrix mechanics produced accurate predictions for atomic behavior, but the mathematics was notoriously difficult to visualize. Even many physicists who accepted the theory found it deeply abstract. It described nature successfully, yet it did so without providing a comfortable mental picture of what electrons were actually doing. Around the same time, another approach emerged from the work of the Austrian physicist Erwin Schrödinger. Schrödinger believed that electrons might behave more like waves than tiny particles. Inspired partly by earlier ideas from Louis de Broglie, who suggested that matter could possess wave-like properties, Schrödinger developed an equation describing how a wave function evolves through time. The wave function became one of the central ideas of quantum mechanics. It is a mathematical description that encodes all the possible states a quantum system might occupy. Instead of telling us exactly where a particle is located, the wave function provides information about the probabilities of finding that particle in different places. Schrödinger's equation allowed physicists to calculate how these probabilities change as a system evolves. Although Schrödinger's wave mechanics looked very different from Heisenberg's matrix mechanics, the two approaches turned out to be mathematically equivalent. Both produced identical predictions for physical experiments. They were simply different mathematical languages describing the same underlying quantum reality. At this stage, however, a profound question remained unanswered. What exactly did the wave function represent? The answer proposed by Max Born introduced one of the most radical shifts in scientific thinking. Born suggested that the wave function should not be interpreted as a physical wave in space, but instead as a mathematical description of probability. In this view, the square of the wave function gives the probability of finding a particle at a particular location when a measurement is performed. This interpretation meant that quantum mechanics does not predict single outcomes with certainty. Instead, it predicts the likelihood of different possible outcomes. Nature itself appears to behave probabilistically at very small scales. This idea unsettled many physicists. Classical science had always assumed that if one knew the initial conditions of a system precisely enough, its future behavior could be predicted exactly. Quantum mechanics seemed to suggest that even with complete information, only probabilities could be calculated. The act of measurement itself began to occupy a central role in the theory. One of the key figures attempting to interpret these ideas was Niels Bohr, working at the Institute for Theoretical Physics in Copenhagen. Together with Werner Heisenberg and other collaborators, Bohr helped develop what became known as the Copenhagen interpretation of quantum mechanics. According to this interpretation, the wave function represents a set of possibilities. When a measurement is made, those possibilities collapse into a single definite outcome. Before the measurement, the system exists in a superposition of states. After the measurement, only one state remains. The Copenhagen interpretation does not attempt to describe what happens between measurements in a classical sense. Instead, it accepts that quantum systems behave according to rules that do not always align with everyday intuition. Some physicists embrace this view as the most practical way to interpret the mathematics. Others were far less comfortable. Louis de Broglie, who had proposed that matter behaves like waves, suggested that particles might still possess definite positions guided by a hidden wave structure. His idea would later be revived and expanded by David Bohm in what became known as pilot wave theory. In this framework, particles follow precise trajectories guided by an underlying quantum wave. David Bohm's interpretation attempted to restore determinism to quantum physics while still reproducing the predictions of the standard theory. Although it never became the dominant interpretation, it demonstrated that alternative conceptual frameworks could exist beneath the same mathematical structure. Another physicist who contributed significantly during this period was Paul Dirac. Dirac possessed an extraordinary ability to uncover elegant mathematical relationships within complex theories. In 1928, he developed the Dirac equation, which combined quantum mechanics with Einstein's theory of special relativity. Dirac's equation predicted something astonishing. It suggested the existence of particles identical to electrons but carrying opposite electric charge. At the time, no such particle had ever been observed. Several years later, the physicist Carl Anderson discovered the positron in cosmic ray experiments, confirming Dirac's prediction. This discovery marked one of the earliest examples of a particle predicted purely through theoretical reasoning before being observed experimentally. Dirac's work also helped establish the foundations of quantum field theory. In this framework, particles are understood not as isolated objects but as excitations of underlying fields that fill space. Electrons arise from an electron field. Photons arise from an electromagnetic field. This perspective would later become central to modern particle physics. Within these mathematical frameworks, another surprising feature began to appear. When physicists described systems containing more than one particle, the wave function no longer described each particle independently. Instead, it described the entire system as a single entity. Two particles that interact and then separate may continue to share one combined wave function. Their properties cannot always be described separately. The mathematics does not treat them as two independent objects. It treats them as parts of a single unified system. This idea emerged naturally from the structure of quantum mechanics. When the wave function for a multi-particle system cannot be written as a simple product of individual particle states, the particles are said to be entangled. At this stage, entanglement was not widely discussed as a central concept. It appeared simply as a mathematical consequence of the theory. Yet the implications were extraordinary. If two particles share a single wave function, then measuring one particle may instantly determine the properties of the other. Even if those particles are separated by enormous distances, the mathematical relationship between them remains intact. For many physicists of the 1920s, these implications were not immediately obvious. Quantum mechanics was still a young theory, and much of the effort focused on solving practical problems such as atomic structure, chemical bonding, and radiation. Yet quietly, hidden within the equations, the seeds of a profound mystery had already been planted. The mathematical language developed by Heisenberg, Schrodinger, Bohr, Dirac, and their colleagues had revealed a universe where physical systems could no longer be treated as entirely separate objects. Instead, nature seemed capable of linking distant particles through a shared quantum description. The consequences of this realization would take decades to fully unfold, but even at this early stage, one thing had become clear. The microscopic world obeys rules that are far stranger than anyone had imagined just a generation earlier. Once quantum mechanics had taken shape during the 1920s, physicists began exploring what the theory actually implied when more than one particle was involved. At first, the focus of the new theory had been on individual atoms and electrons. Schrödinger's equation could describe the energy levels of hydrogen. Matrix mechanics could reproduce the spectral lines seen in experiments. These early successes were remarkable, but they involved relatively simple systems. The deeper mysteries began to appear when scientists started asking what happens when several quantum particles interact with each other. In classical physics, the answer would have been straightforward. If two objects collide and then move apart, each object carries away its own properties. Once separated, their future behavior depends only on their individual states. Two billiard balls that strike each other on a table may exchange momentum, but once they roll away, they behave independently. Quantum mechanics does not always follow that logic. Within the mathematical framework of quantum theory, particles that interact can become linked through a shared description. The wave function used to describe a system does not necessarily break neatly into pieces for each particle. Instead, the wave function can describe the entire system as one unified object. This idea began to emerge as physicists explored the mathematics more carefully. One of the important figures involved in clarifying the mathematical structure of quantum mechanics was John von Neumann. Von Neumann was a brilliant mathematician who worked closely with physicists during the early development of quantum theory. In the 1930s, he provided a rigorous mathematical foundation for quantum mechanics, organizing its ideas within a formal structure that became central to the theory. In von Neumann's formulation, quantum states are represented within an abstract mathematical framework known as Hilbert space. Despite the intimidating name, the basic concept can be explained in simple terms. Hilbert space is a mathematical environment that allows physicists to represent all possible states of a quantum system. Each possible state corresponds to a point within this abstract space. For a single particle, the wave function describes the probabilities associated with different measurable properties, such as position or momentum. When a second particle is added to the system, the description does not simply become two separate wave functions sitting side by side. Instead, the combined system occupies a new space that includes all possible joint configurations of both particles together. This is where things begin to behave very differently from classical expectations. In many situations, the combined wave function of two particles can be written as a product of two separate functions. One describes the first particle, the other describes the second. In those cases, the particles behave independently, just as classical intuition would suggest. But quantum mechanics also allows a different possibility. Sometimes the combined wave function cannot be separated into independent pieces. Instead, the mathematical description only exists as a single unified state, involving both particles simultaneously. When this happens, the properties of one particle cannot be fully described without referencing the other. This situation was examined by several early contributors to quantum mechanics, including Pascual Jordan, who worked with Max Born and Werner Heisenberg in developing matrix mechanics. Jordan explored how quantum operators behave when applied to systems containing multiple interacting particles. These investigations revealed that correlations between particles could arise directly from the structure of the theory itself. Imagine two particles that interact in a way that links one of their properties. A simple example involves a property known as spin. Spin is a form of intrinsic angular momentum carried by many particles, including electrons. If two electrons are produced together in a certain quantum process, the laws of conservation may require that their spins add up to a particular total value. One electron might end up with spin oriented upward, while the other must point downward. In classical thinking, each particle would possess its own definite spin from the moment they separate. Quantum mechanics describes the situation differently. Instead of assigning fixed values immediately, the combined system can exist in a superposition of possibilities. Both outcomes remain possible until a measurement occurs. The wave function describing the pair contains all allowed configurations simultaneously. What matters is that the two particles share a single combined description. If a measurement is later performed on one particle, and its spin is found to be upward, the mathematics immediately determines that the other particle must have spin downward. If the first measurement produces the opposite result, the second particle must match accordingly. The key point is that the second particle's state was not independently determined beforehand. Both outcomes existed within the shared wave function. Physicists slowly began to recognize that these correlations were not unusual exceptions within the theory. They appeared repeatedly whenever interacting quantum systems were examined, and they did not disappear when the particles moved apart. In fact, the equations predicted that these correlations would persist regardless of distance. Once the particles shared a joint wave function, their properties remained mathematically linked even if they travelled far from each other. At first, this did not immediately alarm researchers. Many physicists assumed that the correlations would fade as systems interacted with their surroundings, or that some deeper mechanism would eventually explain them. But the mathematical formalism itself contained no obvious distance limit. Within Hilbert space, the wave function describing the system simply evolves according to Schrödinger's equation. If two particles are entangled within that description, their relationship remains encoded in the state of the system. This meant that the strange correlations were not artificial additions to the theory. They were built directly into its foundations. Whenever physicists wrote down the wave function for a system containing multiple particles, the possibility of these inseparable states appeared naturally. No extra assumptions were required. The mathematics produced them automatically. Over time, it became clear that this feature was not a minor technical detail. It was one of the most distinctive aspects of quantum mechanics. Particles could share information about each other in a way that classical physics had never imagined. Two objects that once interacted could remain connected through their joint quantum state even after travelling enormous distances apart. Their properties would continue to reflect a relationship encoded in the mathematics of the system. This strange behaviour did not arise from experimental tricks or unusual laboratory setups. It emerged directly from the equations that successfully described atoms, molecules, and radiation. In other words, the phenomenon later called entanglement was not invented to make the theory more dramatic. It was discovered hiding quietly inside the mathematics all along, and as physicists began to appreciate the implications of these shared quantum states, a profound question started to take shape. If the equations of quantum mechanics were correct, then nature itself seemed capable of linking distant particles in ways that defied ordinary ideas about separation and independence. The universe, it appeared, might not always treat objects as truly separate things. Sometimes, even when particles drift far apart, the deeper structure of reality continues to treat them as parts of the same system. By the early 1930s, quantum mechanics had proven itself extraordinarily successful. The theory explained atomic spectra with remarkable precision. It described the structure of atoms, the behavior of electrons in materials, and the interaction between light and matter. Predictions made by the equations repeatedly matched experimental measurements. From a practical standpoint, the theory worked beautifully, but not everyone was comfortable with what it implied. One of the most famous skeptics was Albert Einstein. Einstein had played a crucial role in the early development of quantum theory. His explanation of the photoelectric effect in 1905 helped establish the idea that light could behave as discrete particles called photons. Yet as quantum mechanics matured during the 1920s, Einstein grew increasingly uneasy with the philosophical direction the theory seemed to take. At the heart of Einstein's concern were two deeply held principles about how the universe should behave. The first principle was realism. In Einstein's view, physical properties such as position, momentum, and spin should exist independently of whether anyone happens to measure them. A particle should possess definite characteristics whether or not an experimenter observes it. The second principle was locality. According to Einstein's theory of relativity, no influence should travel faster than the speed of light. Events occurring in one location should not instantly affect events happening far away. These principles had guided Einstein's thinking throughout his career. They formed part of the conceptual foundation of modern physics. Quantum mechanics, however, seemed to challenge both. Within the standard interpretation of quantum theory, a particle does not always possess definite properties prior to measurement. Instead, the wave function describes a range of possible outcomes. Only when a measurement occurs does the system settle into one specific result. To Einstein, this sounded less like physics and more like an incomplete description of reality. He suspected that quantum mechanics might be missing some deeper layer of hidden information. Perhaps the theory was correct as far as it went, but maybe it was not the full story. In 1935, Einstein decided to explore this possibility more carefully with two colleagues at the Institute for Advanced Study in Princeton. Their names were Boris Podolsky and Nathan Rosen. Together they wrote a paper that would become one of the most famous challenges ever directed at quantum mechanics. The paper is now known simply as the Einstein-Podolsky-Rosen paradox. The goal of the paper was not to destroy quantum mechanics, but to demonstrate that the theory might be incomplete. The argument began by considering a pair of particles that interact and then move apart. According to quantum mechanics, such particles can share a single combined wave function. Their properties may remain correlated even after they are separated by large distances. Einstein, Podolsky, and Rosen imagined a situation in which two particles were produced together in such a way that certain properties were linked by conservation laws. For example, suppose the total momentum of the pair must equal a fixed value. If one particle later turns out to have a particular momentum, the other particle must automatically possess the corresponding value that preserves the total. Quantum mechanics describes this situation using a shared wave function that includes both particles. Now imagine that the particles drift far apart. One particle might travel to a laboratory on Earth, while the other moves far away in another direction. Eventually, an experimenter measures the momentum of the first particle. Instantly, the theory allows the momentum of the second particle to be known. From Einstein's perspective, this raised a troubling question. If the second particle's momentum can be predicted with certainty without touching it, then that momentum must already be a real property of the particle. Otherwise, the measurement performed on the first particle would somehow have to influence the second particle instantly across space. Such an instantaneous influence would violate the principle of locality. Einstein found this idea unacceptable. Instead, he suggested that quantum mechanics must be missing additional variables that determine the properties of particles in advance. These hypothetical quantities became known as hidden variables. In this view, the apparent randomness of quantum measurements might simply reflect our ignorance of deeper underlying parameters. If those hidden variables were known, the outcomes of quantum experiments might become completely predictable. The Einstein-Podolsky-Rosen argument therefore proposed a simple conclusion. If quantum mechanics allows the prediction of a physical quantity with certainty without disturbing the system, then that quantity must correspond to an element of reality. Since quantum mechanics does not assign definite values to all such quantities simultaneously, the theory must be incomplete. The paper sparked immediate debate within the physics community. Many researchers, including Niels Bohr, defended the standard interpretation of quantum mechanics. Bohr argued that the Einstein-Podolsky-Rosen argument misunderstood the role of measurement in quantum theory. According to Bohr, physical properties cannot be defined independently of the experimental setup used to measure them. In Bohr's view, quantum mechanics was not incomplete. It simply described nature in a way that required abandoning classical ideas about independent properties. Not everyone was satisfied with either side of the debate. Erwin Schrödinger, who had helped develop wave mechanics, found the situation both fascinating and unsettling. Schrödinger wrote several papers exploring the strange correlations highlighted by the Einstein-Podolsky-Rosen argument. In doing so, he introduced a new term that would eventually become central to modern physics. He called the phenomenon quantum entanglement. Schrödinger recognized that when two particles share a combined quantum state, their individual properties cannot always be described separately. The system behaves as a single entity, even when its parts are far apart. This idea struck him as deeply significant. At the same time, mathematicians such as Hermann Weyl examined the conceptual foundations of quantum theory from a more abstract perspective. Weyl studied the symmetry structures underlying quantum mechanics and explored how the mathematical formalism reshaped the meaning of physical observables. These discussions revealed that the debate surrounding quantum mechanics was not simply technical, it was philosophical as well. Physicists were no longer just calculating trajectories or energy levels. They were confronting fundamental questions about the nature of reality itself. Does the universe possess definite properties, independent of observation? Can distant events influence one another instantly? Is quantum randomness a fundamental feature of nature, or merely a sign that a deeper theory remains hidden? Einstein remained convinced that quantum mechanics was incomplete. He famously remarked that he could not believe the universe played dice. Yet despite his doubts, the theory continued to succeed experimentally. The Einstein-Podolsky-Rosen paradox did not immediately settle the debate. Instead, it sharpened the question. If quantum mechanics truly allowed distant particles to share linked properties, then either nature permits non-local connections, or some deeper hidden variables must exist beneath the theory. For many years, there was no clear way to decide between these possibilities. The puzzle would remain unresolved for decades, but the challenge posed by Einstein and his collaborators had accomplished something important. It forced physicists to confront the strange implications of quantum mechanics directly, and it transformed a quiet mathematical curiosity into one of the deepest mysteries in modern science. When Albert Einstein, Boris Podolsky, and Nathan Rosen published their famous argument questioning the completeness of quantum mechanics in 1935, the paper immediately captured the attention of physicists around the world. Many researchers began examining the problem carefully, trying to understand whether the strange correlations predicted by quantum theory represented a genuine feature of nature or simply a misunderstanding of the mathematics. Among those who responded most thoughtfully was Erwin Schrödinger. Schrödinger had already played a central role in the development of quantum mechanics through his wave equation. His work had introduced the wave function as a central object within the theory, describing how quantum systems evolve through time. Now he turned his attention to the conceptual implications of the Einstein-Podolsky-Rosen argument. Rather than dismissing the puzzle, Schrödinger recognized that it revealed something deeply important about quantum theory. In a series of papers written shortly after the Einstein-Podolsky-Rosen publication, Schrödinger examined the mathematical structure of multi-particle quantum systems. He carefully analysed how the wave function behaves when two or more particles interact and then separate. What he discovered was that the strange correlations described by Einstein and his colleagues were not accidental quirks of the theory. They were built directly into its foundations. When two particles interact in certain ways, the combined wave function describing them can become inseparable. The system can no longer be described as two independent objects with separate states. Instead, the wave function represents a single joint description that includes both particles simultaneously. Even if the particles later move far apart, the shared wave function continues to describe the pair as one unified system. Schrodinger realized that this was not a small technical detail hidden inside complicated equations. It was a defining characteristic of quantum mechanics. To describe this phenomenon, Schrodinger introduced a new term. He called it quantum entanglement. The word was chosen deliberately. In everyday language, something entangled is twisted together or tightly connected in a way that cannot easily be separated. Schrodinger believed the same idea captured the relationship between quantum particles that share a combined state. Once entangled, the properties of those particles could no longer be described independently. Their physical descriptions became intertwined. Schrodinger found this idea both fascinating and unsettling. In his writings, he noted that entanglement appeared to be not just one possible feature of quantum mechanics, but perhaps the most distinctive one. He described it as the characteristic trait of quantum theory. To understand why this was so striking, consider how classical physics normally treats objects. In classical systems, each object carries its own properties. A baseball thrown across a field has a position, a velocity, and a trajectory that belong to that baseball alone. Even if the ball once collided with another object, the two objects quickly go their separate ways. Quantum mechanics allows something quite different. When particles become entangled, their properties cannot always be assigned individually. Instead, the system must be described as a whole. The information about the system is stored in the relationships between its parts, rather than within the parts themselves. Imagine two particles created together in a process that links their spins. The combined system may exist in a superposition, where both possible arrangements of spin are present simultaneously. One possibility is that the first particle has upward spin while the second has downward spin. The other possibility is that the first particle has downward spin while the second has upward spin. Before a measurement occurs, the wave function contains both possibilities at once. If a measurement is later performed on one particle, and its spin is found to be upward, the wave function immediately resolves so that the other particle must be downward. What makes this situation so unusual is that the second particle's state was not independently determined beforehand. Instead, the outcome arises from the shared structure of the entangled system. For Schrodinger, this suggested that quantum systems might possess a deeper level of interconnectedness than classical physics had ever imagined. In some sense, the identity of each particle becomes partially defined by its relationship with the other. This realization pushed the discussion of quantum mechanics into philosophical territory. If entangled particles cannot be described independently, then the classical idea of separate objects with separate properties may not always apply at the smaller scales of nature. Reality itself might be organized in ways that differ dramatically from everyday intuition. Schrodinger also recognized that entanglement was closely connected to another mystery within quantum mechanics, the role of measurement. According to the standard interpretation developed by Niels Bohr and Werner Heisenberg, quantum systems exist in superpositions of possibilities until a measurement occurs. The act of observation forces the system into a definite outcome. When entanglement is involved, this process becomes even more puzzling. Measuring one particle in an entangled pair appears to determine the state of the other particle as well. The wave function describing the pair collapses into a specific configuration that resolves both particles simultaneously. From a classical perspective, this behavior seems almost magical. Yet Schrodinger emphasized that the mathematics of quantum mechanics describes it naturally. The theory does not require any signal traveling between the particles. Instead, the shared wave function already contains the information linking their possible outcomes. The measurement simply reveals which possibility becomes real. Schrödinger's reflections did not settle the debate about whether quantum mechanics was complete. Einstein continued to argue that hidden variables might still exist beneath the theory. Others defended the Copenhagen interpretation, accepting the probabilistic nature of the wave function as a fundamental feature of reality. What Schrodinger achieved, however, was something equally important. He gave physicists a clear way to talk about the strange correlations predicted by quantum theory. By naming the phenomenon entanglement, he transformed a confusing mathematical property into a concept that could be studied, debated, and eventually tested through experiment. Over time, researchers would discover that entanglement was not merely a philosophical curiosity. It would become central to modern quantum technologies, including quantum cryptography, quantum computing, and quantum teleportation. But during the 1930s, these practical applications were still far in the future. At that moment, entanglement remained primarily a profound conceptual puzzle. It suggested that when quantum systems interact, the universe may weave their properties together in ways that persist long after the particles themselves drift apart. The deeper implications of that idea would take decades to unfold, yet Schrödinger had already glimpsed something remarkable. The smallest pieces of the universe may not always exist as isolated objects. Sometimes, even across great distances, they remain quietly and invisibly linked. At the heart of quantum mechanics lies an idea that seems simple at first glance, and yet turns out to be one of the strangest features of the microscopic world. This idea is known as quantum superposition. In everyday life, objects exist in clearly defined states. A coin resting on a table is either heads or tails. A light switch is either on or off. A planet is located at one position in space, rather than several different positions at once. Quantum systems do not always follow this pattern. According to quantum mechanics, a particle can exist in multiple possible states simultaneously until a measurement takes place. These possibilities are not simply unknown to us. Instead, the particle genuinely occupies a superposition of states described by its wave function. To picture this idea, imagine a simple system such as the spin of an electron. Spin is an intrinsic form of angular momentum carried by many quantum particles. It behaves somewhat like the orientation of a tiny magnetic compass needle. When measured along a particular direction, an electron's spin can take one of two values. The measurement may reveal that the spin points upward relative to the chosen direction, or downward. Classically, one might assume that the electron always possesses one of these orientations. The measurement simply reveals which one was already there. Quantum mechanics describes the situation differently. Before the measurement occurs, the electron may exist in a superposition of both spin orientations at once. Its wave function contains a combination of the upward possibility and the downward possibility. Only when an experiment is performed does the system produce a definite outcome. This superposition is not merely a philosophical interpretation. It arises directly from the mathematics used to describe quantum systems. Physicists represent quantum states using mathematical objects known as vectors within Hilbert space. Each possible state of a particle corresponds to a direction within this abstract space. Superposition occurs when two or more of these possibilities are combined into a single state. For example, the spin of an electron can be represented by a quantum state that blends the upward and downward possibilities together with particular probabilities. When a measurement takes place, the outcome is determined according to those probabilities. A similar concept appears in experiments involving light. Photons, the particles of light, possess a property known as polarization. Polarization describes the orientation of the electromagnetic wave associated with the photon. A photon can be polarized vertically, horizontally, or at angles in between. Yet quantum mechanics allows a photon to exist in a superposition of polarization states. Before a measurement is performed, the photon may contain multiple possible orientations simultaneously. When the photon passes through a polarizing filter, aligned in a particular direction, the wave function collapses and a specific result appears. These ideas may seem unusual, but they have been confirmed through countless experiments involving atoms, photons, and electrons. Superposition is not limited to individual particles. It also appears in systems containing several interacting particles. When two quantum particles interact, their combined wave function can form a joint description that includes both systems at once. Instead of assigning separate wave functions to each particle, the theory describes them as a single composite system. This combined description allows entirely new possibilities. If two particles share a joint wave function, their states may become linked in such a way that neither particle can be fully described on its own. The mathematical description of one particle depends directly on the state of the other. This situation is precisely what gives rise to quantum entanglement. The concept becomes clearer when examining pairs of particles produced in certain physical processes. For example, when a particle decays into two smaller particles, the conservation laws governing energy, momentum, and angular momentum impose strict constraints on the pair. If the total spin of the system must equal zero, then the spins of the two particles must always be opposite. Quantum mechanics describes this pair using a superposition of possibilities. One possibility is that the first particle has upward spin while the second has downward spin. Another possibility is that the first particle has downward spin while the second has upward spin. Before measurement, both possibilities coexist within the wave function. When an experiment measures the spin of one particle, the result immediately determines the spin of the other. The joint wave function collapses into one of the allowed configurations. The remarkable point is that the two particles behave as parts of a single quantum system, even if they travel far apart. These ideas attracted the attention of several physicists interested in the philosophical implications of quantum mechanics. One such figure was Eugene Wigner. Wigner explored the role of measurement and observation in quantum systems, considering how the act of measurement interacts with the wave function describing a system. Wigner even proposed thought experiments suggesting that consciousness itself might play a role in the collapse of the wave function, although this idea remains controversial and is not widely accepted today. Another important contributor to discussions about quantum measurement was Leon Rosenfeld. Rosenfeld worked closely with Niels Bohr and helped develop the philosophical interpretation of quantum theory associated with the Copenhagen school. Rosenfeld emphasized that measurement cannot be separated from the experimental context in which it occurs. According to this view, quantum systems must be understood through their interactions with measuring devices rather than as isolated objects possessing definite properties at all times. These debates highlighted a deeper question that continues to occupy physicists and philosophers alike. What does the wave function actually represent? Is it a physical entity describing reality itself, or is it simply a tool for predicting the outcomes of measurements? Different interpretations of quantum mechanics answer this question in different ways. Yet regardless of interpretation, the mathematical structure of the theory leads naturally to the same conclusion. When particles interact, their quantum states may merge into a single description, and when that happens, the resulting system may exhibit correlations that cannot be explained by treating the particles independently. In other words, entanglement is not something added to quantum mechanics as a special feature. It emerges directly from the principle of superposition combined with the structure of multiparticle wave functions. Whenever quantum states combine and share information about each other, entanglement becomes possible. This means that the strange connections described by Schrodinger and questioned by Einstein are not rare exceptions. They are natural consequences of the theory itself. The microscopic world appears to operate according to rules in which possibilities coexist, probabilities shape outcomes, and particles may share states that bind them together across space. From the perspective of classical physics, this behavior seems almost impossible. Yet within the framework of quantum mechanics, it is simply how nature works. For many years after the debates sparked by Albert Einstein, Boris Podolsky, and Nathan Rosen, the strange correlations predicted by quantum mechanics remained largely philosophical territory. Physicists argued about them in papers and lectures, but there was no clear way to test whether Einstein's idea of hidden variables or the standard interpretation of quantum mechanics was correct. The problem seemed almost impossible to resolve experimentally. If quantum mechanics predicted correlations between distant particles, perhaps hidden variables were secretly determining those outcomes in advance. Alternatively, perhaps the quantum description was complete, and nature truly behaved in ways that defied classical expectations. For decades, no experiment appeared capable of deciding between these possibilities. Then, in the early 1960s, a physicist from Northern Ireland named John Bell found a way to turn the debate into something testable. Bell had been fascinated by the conceptual puzzles surrounding quantum mechanics since his student days. While working at the European Organization for Nuclear Research, often called CERN, he began studying the Einstein-Podolsky-Rosen argument more carefully. Bell realized that the disagreement between Einstein and the defenders of quantum mechanics revolved around two specific assumptions. The first assumption was locality. According to the theory of relativity developed by Einstein himself, no physical influence should travel faster than the speed of light. Events occurring in one location cannot instantly affect events happening far away. The second assumption was realism. This idea states that physical properties exist whether or not they are measured. A particle should possess definite characteristics even if no experimenter happens to observe them. Einstein believed both of these principles must remain true. Quantum mechanics, however, seemed to threaten them. Bell's key insight was that if hidden variables existed and obeyed the principle of locality, then there would be strict mathematical limits on the correlations that could appear between distant particles. These limits became known as Bell inequalities. Bell derived these inequalities by imagining pairs of particles that share correlated properties, such as spin or polarization. Suppose two particles are produced together and then travel in opposite directions. Each particle eventually reaches a detector that measures one of its properties along a chosen direction. If hidden variables predetermine the outcomes locally, the correlations between measurements performed at different angles would obey certain numerical limits. Those limits arise simply from the rules of probability applied to systems with pre-existing properties. Quantum mechanics predicted something different. When entangled particles are described using the wave function, the correlations between their measurement outcomes can exceed the limits imposed by Bell inequalities. In other words, quantum theory allows stronger correlations than any local hidden variable model could produce. This was a remarkable result. Bell had shown that the debate about hidden variables was not just philosophical after all. It could be decided by experiment. If experiments obeyed Bell inequalities, Einstein's intuition about hidden variables might be correct. But if the inequalities were violated, then the universe would behave in a way that cannot be explained by any theory combining locality and hidden variables. Bell himself expressed the result with striking clarity. Either the world is not governed by local hidden variables, or the predictions of quantum mechanics must fail. For the first time, physicists had a way to test the strange implications of entanglement directly. Bell's work did not remain isolated. Other researchers soon began exploring the implications of his theorem in greater detail. Among them were physicists Abner Shimoni and Michael Horn, who helped develop refined versions of Bell inequalities suitable for real laboratory experiments. Working alongside John Clauser and others, they explored how entangled photon pairs could be used to measure these correlations in practice. These collaborations eventually produced what is now called the Clauser-Horn-Shimony-Holt inequality. This version of Bell's inequality proved particularly useful for experimental tests involving light and polarization measurements. The mathematics behind these inequalities is elegant but conceptually straightforward. Imagine measuring the polarization of two entangled photons using detectors oriented at different angles. If hidden variables determine the outcomes in advance, the statistical correlations between measurements must fall within certain boundaries. Quantum mechanics predicts that in specific arrangements, the correlations will exceed those classical limits. The difference between the two predictions is not small. Under the right conditions, the quantum correlations can be significantly stronger. This meant that careful experiments could settle the question. Bell's theorem carried profound philosophical consequences. If experiments violated Bell inequalities, it would mean that at least one of Einstein's cherished assumptions must be abandoned. Either the world does not obey locality in the strict classical sense, or the idea that particles possess definite properties before measurement must be reconsidered. In fact, Bell himself often emphasized that the theorem forces physicists to rethink the nature of reality. The universe, it seems, may allow connections between distant systems that cannot be explained through classical mechanisms operating locally in space. This does not mean that signals or information travel faster than light. Quantum mechanics still obeys the overall constraints of relativity when it comes to communication. Entanglement cannot be used to send messages instantaneously, but it does mean that the structure of reality may contain correlations that extend across space in ways classical physics never anticipated. Bell's work therefore accomplished something extraordinary. For decades, entanglement had been treated largely as a philosophical puzzle, raised by Einstein and explored by Schrodinger. It existed mostly within discussions about the meaning of quantum theory. Bell transformed that discussion. He showed that the strange correlations predicted by quantum mechanics could be tested experimentally using real particles and real detectors. The debate was no longer confined to blackboards and thought experiments. It could now be carried into the laboratory. Once Bell's theorem appeared, physicists around the world began preparing experiments designed to measure entangled particles with increasing precision. If the results violated Bell inequalities, Einstein's dream of a local hidden variable explanation would face serious trouble. If the inequalities held, quantum mechanics itself might need revision. Either outcome would reveal something fundamental about the nature of the universe. The stage was set for a series of experiments that would eventually transform entanglement from a philosophical curiosity into one of the most powerful tools in modern physics. For several decades after John Bell published his remarkable theorem in the 1960s, the strange implications of quantum entanglement still lived mostly in theoretical papers and philosophical discussions. The mathematics was persuasive, but physics ultimately demands something more than elegant equations. It demands experiments. The challenge was that testing Bell's ideas required extraordinary precision. Researchers needed a way to create pairs of particles that shared a common quantum state, separate them by measurable distances, and then measure their properties in carefully controlled ways. Even small imperfections in the equipment could obscure the subtle, statistical patterns Bell's inequalities predicted. By the late 1960s and early 1970s, advances in experimental technology finally made such tests possible. One of the earliest decisive attempts was carried out by two physicists working in the United States, John Clauser and Stuart Friedman. At the time, Clauser was a young researcher who had been deeply intrigued by Bell's theorem and the possibility of testing it experimentally. Together with Friedman at the University of California, Berkeley, Clauser designed an experiment using entangled photons produced during atomic transitions in calcium atoms. When certain atoms release energy, they can emit two photons in quick succession. Quantum mechanics predicts that under the right conditions, these photons will share an entangled polarization state. Polarization describes the orientation of the oscillations in a light wave. For entangled photons, measurements of polarization performed at different angles should produce correlations stronger than those allowed by any local hidden variable theory. Clauser and Friedman set up detectors positioned along different orientations and carefully recorded the results of thousands of photon pairs. Their goal was to measure whether the observed correlations violated Bell's inequality. In 1972, the experiment produced its answer. The correlations between the photon measurements exceeded the classical limits predicted by local hidden variable theories. Instead, they matched the predictions of quantum mechanics. Although the experiment contained certain technical limitations, the result was striking. For the first time, laboratory measurements appeared to confirm that entangled particles behave exactly as quantum theory predicts. The outcome did not immediately settle every doubt. Some physicists pointed out potential experimental loopholes that might still allow classical explanations. These loopholes involved subtle issues such as detector efficiency and the possibility that hidden variables might influence which particle pairs were actually detected. Nevertheless, the Clauser-Friedman experiment marked a turning point. Entanglement was no longer just a theoretical curiosity. It had entered the realm of measurable physics. Over the following decade, experimental techniques improved dramatically. One of the scientists who played a central role in refining these tests was the French physicist Alain Aspect. Aspect worked at the Institut d'Optique near Paris and became fascinated by Bell's theorem during the late 1970s. He realized that by using more advanced experimental methods, it might be possible to address many of the criticisms raised against earlier tests. Aspect and his colleagues designed a series of increasingly sophisticated experiments involving entangled photons produced by excited calcium atoms. These photons were sent toward two separate detectors that measured their polarization. The crucial innovation involved rapidly changing the orientation of the detectors while the photons were already in flight. This was an important step because it prevented any hypothetical hidden variables from coordinating the measurement outcomes in advance. If the detector settings could change faster than any signal traveling at the speed of light could communicate between them, then classical explanations based on local influences would become extremely difficult to maintain. Aspect's team achieved this by using fast-switching devices capable of altering detector orientations in extremely short time intervals. The results were published in the early 1980s and proved to be remarkably clear. Once again, the observed correlations violated Bell inequalities. The measurements aligned precisely with the predictions of quantum mechanics. These experiments demonstrated that entangled photons exhibit correlations stronger than any theory based on local hidden variables can allow. In other words, nature itself seemed to follow the strange rules described by quantum mechanics. Aspect's experiments attracted enormous attention within the physics community. Many researchers regarded them as the most convincing demonstration yet that entanglement was a genuine physical phenomenon rather than a mathematical artifact. The results also highlighted how technological progress often drives scientific discovery. Producing entangled photon pairs reliably required stable lasers, carefully designed optical crystals, and extremely sensitive detectors capable of registering individual photons. Each improvement in equipment allowed researchers to test Bell's inequalities with greater precision. Laser technology in particular played a crucial role. Highly coherent beams of light made it possible to generate entangled photons through processes such as spontaneous parametric down conversion in non-linear crystals. In this process, a single photon entering the crystal can transform into two lower energy photons, whose properties are linked by the rules of quantum mechanics. These photon pairs emerge already entangled. Using optical components such as polarizing filters and beam splitters, physicists can direct the photons towards separate detectors positioned meters apart or even farther. By rotating the orientation of the detectors, researchers measure how the polarization correlations change with angle. The statistical patterns that appear in these measurements provide a direct test of Bell inequalities. As detector technology improved, experiments began achieving extraordinary levels of precision. Photomultiplier tubes and later avalanche photodiodes allowed scientists to detect individual photons with increasing efficiency. Electronic timing systems ensured that measurement events could be recorded with remarkable accuracy. With each improvement, the evidence for quantum entanglement grew stronger. By the late 20th century, many laboratories around the world had repeated and extended these experiments. Researchers closed loopholes that had once worried critics, improved detection efficiencies, and increased the distances between detectors. Some experiments separated entangled photons by several kilometers using optical fibers or free space transmission. Even under these conditions, the correlations predicted by quantum mechanics persisted. The implications were profound. The experimental violations of Bell inequalities showed that nature cannot be fully described by any theory combining local realism and hidden variables. At least one of those classical assumptions must give way. Most physicists concluded that the classical picture of independent objects carrying predetermined properties must be reconsidered. Instead, quantum systems appear to possess a deeper kind of connectedness. Two particles that have interacted in the past may remain part of a shared quantum state even after traveling far apart. When a measurement is performed on one particle, the result is correlated with the measurement outcome of the other in ways that cannot be explained by classical influences traveling through space. Importantly, these correlations do not allow faster-than-light communication. The statistical patterns only become apparent when measurement results from both detectors are compared afterward. Nevertheless, the correlations themselves reveal something remarkable about the structure of physical reality. Entanglement is not a rare curiosity confined to abstract equations. It is a measurable, repeatable feature of the natural world. Today, the experiments first performed by Clauser, Friedman, Aspect, and many others are regarded as foundational demonstrations of quantum physics. Their work transformed entanglement from a philosophical puzzle into an experimentally verified phenomenon. In recognition of the profound importance of these achievements, the Nobel Prize in Physics in the early 2020s was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for pioneering experiments with entangled quantum systems. What once seemed like an almost absurd prediction of quantum theory had become one of the most carefully tested principles in modern physics. The universe, it appears, really does allow distant particles to share a connection that defies classical expectations. And those connections would soon become more than just experimental curiosities. They would form the foundation of entirely new technologies based on the strange logic of quantum information. For many years, quantum entanglement was treated almost like a philosophical oddity. It appeared in equations, provoked debates between physicists, and occasionally surfaced in carefully controlled laboratory experiments. But for most of the 20th century, it was not widely considered useful in any practical sense. That perception began to change during the late 20th century. A new generation of physicists started to realize that entanglement was not merely a strange prediction of quantum mechanics. It could actually be used. More specifically, it could function as a physical resource, something that could be created, measured, manipulated, and applied to perform tasks that classical systems simply cannot accomplish. This shift in thinking gave rise to a field now known as quantum information science. Instead of asking only philosophical questions about the meaning of quantum mechanics, researchers began asking something different. If nature allows entangled systems to exist, what kinds of information processing might those systems enable? One of the pioneers of this emerging field was the physicist Charles Bennett, working at IBM in the United States. Bennett was fascinated by the possibility that the laws of quantum mechanics might allow new forms of communication and computation. Around the same time, another important figure entered the picture, the Canadian cryptographer Gilles Brassard. Bennett and Brassard collaborated on one of the earliest proposals for quantum communication systems. Their work focused on the problem of secure information exchange, a topic that has been important throughout human history. From ancient coded messages to modern digital encryption, the challenge has always been the same. How can two people exchange information without an eavesdropper secretly intercepting it? Classical cryptography often relies on mathematical complexity. Encryption systems are designed so that breaking the code would require an impractically large amount of computational effort. Quantum mechanics offered a completely different approach. Because quantum systems change when they are measured, it becomes possible to design communication protocols in which any attempt at eavesdropping leaves detectable traces. In the early 1980s, Bennett and Brassard proposed a protocol now widely known as the BB8-4 protocol. This method uses quantum states of light, such as photon polarization, to generate secret cryptographic keys shared between two parties. If an eavesdropper attempts to intercept and measure the photons, the disturbance introduced by that measurement alters the statistical patterns of the transmission. Those changes reveal the presence of the intruder. The security of this approach does not rely on computational difficulty. Instead, it is guaranteed by the fundamental laws of quantum physics. Shortly afterward, another remarkable idea appeared. In the early 1990s, physicist Arthur Eckert developed a quantum cryptography protocol that relied directly on entanglement itself. Eckert realized that pairs of entangled particles could be used to generate shared random keys between distant observers. Because entangled systems exhibit correlations that violate Bell inequalities, the presence of those correlations can confirm that the communication channel has not been compromised. In essence, Bell's theorem became a tool for cryptographic security. If the observed correlations match the predictions of quantum mechanics, then no classical hidden variable system could be secretly mimicking the results. Any attempt by an eavesdropper to interfere would weaken the correlations and become visible in the data. This approach connected quantum cryptography directly with the deep conceptual foundations of quantum mechanics. At the same time, researchers began developing mathematical tools to describe entanglement more precisely. One of the most important ideas in this area is known as entanglement entropy. Entropy, in physics, generally measures uncertainty or disorder within a system. In the context of quantum information, entanglement entropy quantifies how strongly different parts of a system are correlated with one another. When two particles are not entangled, their quantum states can be described independently. In that case, the entropy associated with their correlation is essentially zero. But when two systems become entangled, their combined state contains information that cannot be separated into independent parts. Measuring one system reveals information about the other. Entanglement entropy measures the degree of that connection. The greater the entanglement entropy, the more deeply the systems are linked at the quantum level. These mathematical tools allowed physicists to treat entanglement as something quantifiable rather than mysterious. It could be measured, compared, and even manipulated in controlled ways. Another powerful concept emerged during this period known as quantum teleportation. Despite the science fiction-sounding name, quantum teleportation does not involve transporting physical objects instantaneously across space. Instead, it refers to the transfer of quantum information from one location to another, using entanglement and classical communication. The protocol was first proposed in the early 1990s by Charles Bennett, along with collaborators including Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters. In this process, an unknown quantum state can be transmitted between two distant systems without physically sending the particle that originally carried the state. Entanglement acts as the essential ingredient that makes this transfer possible. Once again, something that once seemed purely theoretical began to reveal practical applications. Meanwhile, the growing field of quantum computing was also beginning to take shape. Traditional computers store information using bits that exist in one of two possible states, often described as 0 or 1. Quantum computers instead use quantum bits, commonly called qubits, which can exist in superpositions of states. When multiple qubits become entangled, their combined state can represent a vast number of possibilities simultaneously. This property allows quantum algorithms to explore certain computational problems far more efficiently than classical systems. Researchers such as Peter Shor and Love Grover later developed algorithms demonstrating that quantum computers could solve specific tasks, including integer factorization and database searching, dramatically faster than classical machines. Entanglement plays a central role in these processes. Without entanglement, the computational advantages of quantum systems would largely disappear. The shared quantum states allow qubits to coordinate their behavior in ways that classical bits cannot replicate. By the early 21st century, quantum information science had grown into a major research field, spanning physics, computer science, engineering, and mathematics. Laboratories around the world began building experimental quantum processors using technologies such as trapped ions, superconducting circuits, and neutral atoms held in optical traps. Each of these systems attempts to create and maintain entangled states among multiple qubits, long enough to perform useful computations. Maintaining entanglement is not easy. Quantum systems interact constantly with their surrounding environment, and these interactions tend to destroy delicate quantum correlations in a process known as decoherence. Nevertheless, researchers continue to develop new methods for preserving entanglement and correcting errors that arise during computation. Today, entanglement sits at the heart of a rapidly advancing technological frontier. Quantum communication networks are being developed to transmit secure information across long distances. Experimental quantum computers are beginning to perform calculations that push the limits of classical simulation. Quantum sensors use entangled states to achieve extraordinary measurement precision. What began as a puzzling feature of quantum equations has become something far more tangible. Entanglement is now understood as a genuine physical resource, one that can be created, manipulated, and applied to tasks impossible within classical physics. In the process, a phenomenon once dismissed as a philosophical curiosity has evolved into one of the most powerful tools in modern science. And perhaps even more remarkably, these applications still rest upon the same strange principle that puzzled Einstein nearly a century ago. Particles that once interacted may remain linked, sharing a single quantum description even after travelling vast distances apart. The universe, it seems, allows connections deeper than classical intuition ever imagined. One of the most fascinating questions surrounding quantum entanglement has always been how far its strange correlations can reach. In the early laboratory experiments, entangled particles were typically separated by only a few meters inside controlled environments filled with optical equipment, detectors, and delicate electronic timing systems. These early tests already confirmed that entangled particles behave in ways classical physics cannot explain. Yet many physicists wondered whether the phenomenon might break down over larger distances. Perhaps subtle environmental effects would disrupt the fragile correlations once particles were separated by hundreds or thousands of meters. If entanglement truly represented a fundamental feature of nature, it should survive even when particles travel very far apart. Testing that possibility became an important goal for experimental physicists. One of the leading figures in this effort has been the Austrian physicist Anton Zeilinger. Working for many years at the University of Vienna and later at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences, Zeilinger and his collaborators carried out a remarkable series of experiments designed to stretch entanglement across increasingly large distances. During the 1990s and early 2000s, Zeilinger's group began transmitting entangled photons across optical fibers and through open-air paths between distant locations. These experiments often took place across the rooftops of cities or between laboratories separated by several kilometers. The goal was simple but profound. If two photons created together remain entangled even after traveling large distances, their measurement outcomes should continue to exhibit the strong correlations predicted by quantum mechanics. To test this idea, researchers generated entangled photon pairs using nonlinear optical crystals illuminated by carefully tuned laser beams. The process commonly used is called spontaneous parametric down conversion. In this process, a single photon entering a special crystal can split into two lower energy photons that share a linked quantum state. Once created, the photon pair is directed along separate paths. One photon travels toward one detector, while its partner travels toward another detector located some distance away. Each detector measures the polarization of the incoming photon along a chosen orientation. When scientists later compare the results recorded by both detectors, the statistical patterns reveal whether the photons behaved as entangled partners. Zeilinger's experiments repeatedly confirmed that the quantum correlations persist even when the photons travel kilometers apart. The distance between the detectors did not weaken the entanglement in any detectable way. The universe seemed entirely comfortable allowing two particles separated by vast distances to remain part of a single quantum system. Encouraged by these results, physicists began thinking even bigger. Instead of transmitting entangled photons through optical fibers or across city rooftops, why not send them into space? The atmosphere and the curvature of Earth limit the distances over which photons can travel directly through open air. But satellites orbiting above the atmosphere could act as relay stations for quantum signals traveling between distant ground locations. Such a system would allow entangled particles to be distributed across continents. This ambitious idea eventually became reality through an extraordinary international effort led by Chinese physicists. At the center of this effort was a satellite named Micius. The satellite was launched in the mid-2000s by the Chinese Academy of Sciences as part of a broader program exploring quantum communication technologies. Micius was designed specifically to generate and distribute entangled photons between distant locations on Earth. Inside the satellite, specialized optical systems produce pairs of entangled photons. These photons are then directed toward different ground stations separated by thousands of kilometers. One photon travels toward one station while its entangled partner travels toward another. Because the satellite orbits above the atmosphere, the photons can travel through space with minimal interference before reaching their destinations. Once the photons arrive at the ground stations, scientists measure their polarization states using carefully aligned detectors. The results are later compared to determine whether the quantum correlations remain intact. The findings have been extraordinary. Experiments involving the Micius satellite have demonstrated entanglement across distances exceeding 1,000 kilometers. Even at these enormous separations, the measured correlations continue to violate Bell inequalities in exactly the way quantum mechanics predicts. These results confirm that entanglement does not fade with distance. Particles that once interacted can remain connected even when separated by distances comparable to the span of entire countries. In another remarkable demonstration, researchers used the satellite to perform quantum key distribution between distant ground stations. Entangled photons traveling through space allowed secure cryptographic keys to be established between laboratories separated by vast distances. The success of these experiments has helped lay the groundwork for future global quantum communication networks. Yet despite these astonishing results, one important point must always be emphasized. Entanglement does not allow faster-than-light communication. At first glance, the correlations between entangled particles can appear instantaneous. When one particle is measured, the measurement outcome of its distant partner becomes statistically correlated in a way that seems to occur immediately. However, these correlations cannot be used to transmit usable information faster than the speed of light. The reason lies in the statistical nature of quantum measurements. When one observer measures a particle, the result appears random. Only when measurement records from both locations are later compared do the correlations become visible. This comparison requires classical communication, which is limited by the speed of light according to Einstein's theory of relativity. In other words, entanglement produces correlations that are stronger than classical physics allows, but those correlations cannot be used to send messages instantly across space. Relativity remains intact. Nevertheless, the phenomenon remains deeply intriguing. The fact that particles separated by hundreds or even thousands of kilometers can still behave as parts of a unified quantum system challenges everyday intuition about how the universe should work. Space appears to separate objects physically, yet entanglement reveals that some connections extend beyond classical notions of distance. For this reason, many physicists now view entanglement as one of the most profound discoveries in the history of science. Experiments stretching from laboratory tables to orbiting satellites continue to demonstrate the same astonishing conclusion. Two particles that once interacted can remain linked across enormous distances, sharing correlations that cannot be explained by any classical mechanism confined to local space. The universe, it seems, allows relationships that extend far beyond what common sense once considered possible, and with each new experiment pushing the limits of distance and precision, the strange bond of quantum entanglement continues to reveal just how interconnected the fabric of reality may be. Among the many surprising ideas that emerge from the study of quantum entanglement, one of the most famous carries a name that sounds almost like science fiction. The concept is known as quantum teleportation. The phrase often causes understandable confusion. When people hear the word teleportation, the imagination tends to leap immediately toward visions of objects, or even people instantly traveling from one location to another, vanishing in one place and reappearing somewhere else. Quantum teleportation does not work like that. No objects disappear, no bodies are transported across space, and no one is stepping onto glowing platforms waiting to be beamed somewhere else. Instead, quantum teleportation refers to the transfer of the quantum state of a system from one location to another. That difference is subtle but extremely important. In physics, a quantum state contains the full description of a system's measurable properties. For a particle such as a photon or an electron, this state might include properties like polarization, spin orientation, or phase relationships. If one could somehow move that entire quantum description from one particle to another distant particle, the second particle would become an exact replica of the original state. The state would effectively be transferred, even though the physical particle itself never travelled. This remarkable idea was first developed in the early 1990s by a group of physicists led by Charles Bennett at IBM. Bennett worked alongside several collaborators, including Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters. Together, they proposed a protocol demonstrating that entanglement could be used to move quantum information between distant locations. The logic behind the process is clever and elegant. Imagine two distant laboratories that share a pair of entangled particles. One laboratory holds one particle from the pair, while the second laboratory holds the other. Because the particles are entangled, they share a single quantum description even though they are separated in space. Now suppose a third particle exists at the first laboratory. This particle carries a quantum state that scientists want to transfer to the distant laboratory. Directly measuring that particle would destroy its delicate quantum state, so copying it in the usual sense is impossible. Quantum mechanics includes a rule known as the no-cloning theorem, which states that an unknown quantum state cannot be duplicated perfectly. Teleportation circumvents this limitation in a fascinating way. Instead of copying the state, the protocol transfers the state from one particle to another while destroying the original. At the first laboratory, the unknown particle is allowed to interact with the entangled particle already present there. Scientists perform a special joint measurement known as a Bell state measurement. This measurement does not reveal the full quantum state of the original particle. Instead, it produces a small amount of classical information describing how the two particles were related during the measurement. After performing the measurement, the scientists send that classical information to the second laboratory using ordinary communication channels. Because classical communication obeys the speed of light limit, no information travels instantaneously. Once the message arrives, the second laboratory performs a specific transformation on its entangled particle based on the information received. After this transformation is applied, the distant particle takes on the exact quantum state that originally belonged to the particle in the first laboratory. The state has effectively been transferred across space. The original state no longer exists at the first location because the measurement destroyed it. Instead, the quantum information has been recreated at the distant site. This is what physicists mean by quantum teleportation. The protocol demonstrates how entanglement and classical communication can combine to transmit quantum information without physically moving the particle that originally carried it. For several years after the proposal was published, teleportation remained purely theoretical. Researchers understood the mathematics, but performing the experiment required precise control of entangled particles and delicate measurements. That situation changed during the late 1990s. Anton Zeilinger and his research group in Austria carried out some of the earliest successful demonstrations of quantum teleportation using entangled photons. In their experiments, photons created through nonlinear optical processes served as the carriers of quantum information. One photon carried the quantum state to be teleported, while another pair of photons formed the entangled channel between distant locations. Using carefully designed optical equipment, beam splitters, and polarization detectors, the researchers performed the necessary Bell state measurements and applied the corresponding transformations at the receiving end. The results showed that the quantum state of one photon could indeed be transferred to another photon located at a different position. Although the early experiments involved only small laboratory distances, the principle was clear. Quantum information could be transmitted using entanglement. Over time, teleportation experiments became more sophisticated. Researchers extended the technique to other types of quantum systems, including trapped ions, superconducting circuits, and atoms confined in electromagnetic traps. In each case, entanglement served as the bridge allowing quantum states to be transferred between distant systems. The process remains delicate because quantum states are extremely sensitive to environmental disturbances. Even small interactions with surrounding particles or electromagnetic noise can disrupt the fragile correlations required for teleportation. Nevertheless, experimental methods have steadily improved. Today, teleportation has been demonstrated across optical fibers, between distant laboratories, and even between ground stations and orbiting satellites using entangled photons distributed through space. Beyond the experimental demonstrations, the theoretical implications of teleportation continue to inspire new ideas. Physicists such as Seth Lloyd at the Massachusetts Institute of Technology have explored how teleportation protocols might play important roles in future quantum networks and quantum computing architectures. In some theoretical models, teleportation becomes a fundamental method for moving quantum information between distant processors inside a quantum computer. Instead of physically transporting qubits, entangled connections could allow their states to be transferred rapidly between computational nodes. This concept forms part of the broader vision of a quantum internet, a network in which entangled particles link devices across large distances. Such a network could enable ultra-secure communication, distributed quantum computing, and new forms of scientific measurement. Even more speculative research explores how teleportation concepts might illuminate deeper aspects of physics. Some theoretical frameworks in quantum gravity and quantum information theory suggest surprising connections between entanglement and the structure of spacetime itself. In these ideas, the teleportation of quantum information may provide clues about how geometry and quantum mechanics intertwine at fundamental levels. While such ideas remain active areas of research, the core lesson of teleportation is already clear. Entanglement is not merely a philosophical curiosity. It allows information to move in ways that classical physics never anticipated. The universe appears to permit a remarkable process in which the quantum description of a system can be transferred from one location to another without sending the original particle along the journey. No objects vanish and reappear, yet the information that defines their quantum identity can travel through the strange and subtle pathways opened by entanglement. It is a reminder that the deeper one looks into the quantum world, the more surprising the possibilities become. For much of the 20th century, computers were built around a very simple idea. Information could be represented using bits, and each bit could exist in one of two states. In everyday language, those states are often described as 0 and 1. Inside a conventional computer, these states are implemented using tiny electrical signals. A transistor might allow current to flow, representing one state, or block it, representing the other. Billions of these tiny switches work together to perform calculations, store information, and run programs. This approach has been extraordinarily successful. Classical computers have transformed science, engineering, medicine, and nearly every aspect of modern life. Yet classical bits are ultimately limited by the rules of classical physics. Quantum mechanics introduces an entirely different way of representing information. Instead of classical bits, a quantum computer uses units called quantum bits, commonly known as qubits. A qubit is not restricted to a single definite state. Because of the principle of quantum superposition, a qubit can exist in a combination of states simultaneously. In simple terms, a qubit can behave as though it is both 0 and 1 at the same time until a measurement occurs. This property alone already changes the way information can be processed. But the real power of quantum computing appears when multiple qubits become entangled with one another. When qubits are entangled, their states cannot be described independently. Instead, the entire collection of qubits must be treated as a single quantum system. This shared quantum state allows qubits to coordinate their behavior in ways that classical bits never could. To understand why this matters, consider how the number of possible states grows in a quantum system. A classical computer with 2 bits can represent 4 possible configurations, but only one of those configurations exists at any given moment. The system is either 00, 01, 10, or 11. A quantum system with 2 entangled qubits can represent a superposition involving all 4 possibilities simultaneously. As additional qubits are added, the number of possible states grows extremely rapidly. With 10 qubits, a quantum processor can represent over 1,000 possible configurations at once. With 20 qubits, that number exceeds 1 million. As the system grows larger, the amount of information contained within the quantum state expands dramatically. Of course, accessing that information requires carefully designed algorithms. Simply having many possible states available does not automatically solve useful problems. This is where the work of several key physicists becomes important. One of the earliest pioneers in quantum computation was the British physicist David Deutsch. In the 1980s, Deutsch proposed the idea of a universal quantum computer capable of performing calculations using quantum mechanical principles. Deutsch demonstrated that quantum systems could, in principle, simulate physical processes that would be extremely difficult for classical computers to reproduce. His work helped establish the theoretical foundation of quantum computing as a legitimate field of research. The true power of the idea became clear during the 1990s when researchers discovered specific quantum algorithms capable of outperforming classical methods. One of the most famous examples was developed by mathematician Peter Shor. Shor created a quantum algorithm capable of factoring large integers much more efficiently than the best-known classical algorithms. This might sound like a purely mathematical curiosity, but it has enormous implications for cryptography. Many modern encryption systems rely on the difficulty of factoring large numbers. Classical computers would require extremely long times to break such codes. A sufficiently powerful quantum computer running Shor's algorithm could solve the same problem dramatically faster. Another important contribution came from the physicist Love Grover. Grover developed a quantum algorithm capable of searching unsorted databases more efficiently than classical methods. In a classical search, finding a specific item in a list might require checking each entry one by one. Grover's algorithm allows a quantum computer to locate the desired entry using significantly fewer steps. These discoveries demonstrated that quantum computers were not merely theoretical curiosities. They could potentially perform real tasks that classical machines struggle to handle. Building such computers, however, turned out to be extremely difficult. The central challenge lies in maintaining entanglement among many qubits at the same time. Quantum states are extremely delicate. Interactions with the surrounding environment, such as stray electromagnetic radiation or vibrations from nearby equipment, can disrupt the fragile correlations between qubits. This process, known as decoherence, destroys the quantum properties that give quantum computers their power. If decoherence occurs too quickly, the information stored in the quantum state becomes scrambled before useful calculations can be completed. For this reason, researchers must isolate quantum processes from environmental disturbances as much as possible. Different research groups have developed a variety of physical systems to serve as qubits. One approach uses superconducting circuits, which are tiny electrical loops cooled to extremely low temperatures, at temperatures only a fraction of a degree above absolute zero. These circuits can behave according to quantum mechanical principles. Institutions such as IBM Quantum and Google Quantum AI have built experimental processors using superconducting qubits arranged on small chips. These processors are housed inside elaborate cryogenic refrigerators designed to maintain extremely stable conditions. Another approach involves trapping individual ions using electromagnetic fields. In these systems, charged atoms are suspended in vacuum chambers and manipulated using precisely tuned laser beams. The University of Innsbruck in Austria has become one of the leading centers for trapped ion quantum computing. Researchers there have demonstrated high-precision control over entangled ion systems, allowing them to perform complex quantum operations. Each technology comes with its own advantages and challenges. Superconducting circuits can be manufactured using techniques similar to those used in conventional microelectronics, potentially allowing large numbers of qubits to be integrated onto chips. Trapped ions, on the other hand, often exhibit longer coherence times and extremely precise control over quantum states. Despite significant progress, Modern quantum processors still operate with relatively small numbers of qubits, compared to the billions of transistors found in classical computers. Maintaining entanglement across dozens or hundreds of qubits remains a major technical challenge. To overcome these difficulties, researchers have developed methods known as quantum error correction. These techniques distribute quantum information across multiple entangled qubits so that errors caused by decoherence can be detected and corrected without destroying the underlying quantum state. Implementing error correction requires additional qubits and extremely precise control over the entire system. As a result, building large-scale, fault-tolerant quantum computers remains an active area of research. Nevertheless, steady progress continues. Experimental quantum processors have already demonstrated tasks that would be extremely difficult for classical machines to simulate directly. In recent years, researchers at Google Quantum AI reported experiments involving specialized quantum circuits that produced results beyond the reach of conventional supercomputers. While these demonstrations do not yet translate into practical applications, they show that quantum processors are steadily approaching regimes where their capabilities surpass classical limits. At the heart of all these efforts lies entanglement. Without entangled states linking multiple qubits together, quantum computers would behave little differently from classical machines. It is the shared quantum information within these entangled systems that allows quantum algorithms to explore vast computational possibilities simultaneously. In a sense, entanglement acts as the engine driving quantum computation. The strange correlations that once puzzled Einstein have now become essential ingredients in some of the most advanced technologies being developed today. What began as an unsettling prediction of quantum theory has gradually evolved into a powerful tool for processing information in entirely new ways. And although large-scale quantum computers remain under development, the steady progress of laboratories around the world suggests that the era of entangled computation is only just beginning. As experiments with entangled particles became more reliable, physicists began to imagine something far larger than individual laboratory demonstrations. Instead of creating entangled particles only within a single experiment, researchers wondered whether entire communication networks could be built around entanglement itself. This idea gave rise to the concept of quantum networks. In a classical communication network, information travels through electrical signals, radio waves, or optical pulses carrying bits of data. The internet that connects computers around the world works by routing enormous streams of these classical bits through cables, satellites, and wireless systems. Quantum networks aim to do something different. Instead of transmitting classical bits alone, a quantum network distributes entangled quantum states between distant locations. In such a network, laboratories, data centers, or communication nodes would share entangled particles that link them together at the quantum level. These shared states could then be used for extremely secure communication, distributed quantum computing, and advanced sensing technologies. Building such networks requires a combination of many ideas developed over the past several decades. One of the central challenges is distance. Photons traveling through optical fibers gradually lose intensity as they move through the material. Even under ideal conditions, signal losses accumulate over long distances. In classical networks, this problem is solved using devices called amplifiers that boost weakened signals. Quantum information cannot simply be amplified in this way. Because of the no-cloning theorem in quantum mechanics, it is impossible to copy an unknown quantum state perfectly. Amplifying a quantum signal by copying it would violate the fundamental rules of the theory. This limitation means that transmitting entangled states across large distances requires new solutions. One of the most important proposals addressing this challenge came from physicist Hans-Jürgen Briegel and his collaborators during the late 1990s. Briegel introduced the concept of a device known as a quantum repeater. A quantum repeater functions somewhat like a relay station within a network. Instead of sending entangled particles directly across extremely long distances, the communication path is divided into shorter segments. Entanglement is first established between neighboring nodes along the chain. Once entanglement exists within these smaller links, a process called entanglement swapping can extend the connection across larger distances. Entanglement swapping works through a clever sequence of measurements. Imagine two pairs of entangled particles. One particle from each pair is brought together at a central station, while the remaining particles remain at distant locations. When a special joint measurement is performed on the two central particles, something remarkable occurs. The two distant particles which never interacted directly, become entangled with each other. In effect, the entanglement has been extended across a longer distance. By repeating this process across multiple nodes, a chain of quantum repeaters can gradually distribute entanglement across hundreds or even thousands of kilometers. This approach provides a possible blueprint for building large-scale quantum communication networks. Over the past 2 decades, research groups around the world have been working toward this goal. Major international programs have emerged to support the development of quantum technologies. In Europe, the European Quantum Flagship Program was launched to coordinate research across universities, laboratories, and industry partners throughout the continent. The initiative supports projects exploring quantum communication, quantum computing, quantum sensing, and quantum simulation. A significant portion of the program focuses specifically on building prototype quantum networks capable of distributing entangled particles across large distances. In the United States, a similar effort emerged through the National Quantum Initiative. This program supports research conducted by institutions such as the National Institute of Standards and Technology, the Department of Energy National Laboratories, and numerous universities. The National Quantum Initiative aims to accelerate the development of quantum technologies while strengthening the scientific foundations underlying these emerging systems. Across Asia and other regions, additional programs have been launched with similar goals. China has invested heavily in quantum communication research, including the satellite-based experiments that demonstrated entanglement distribution between distant ground stations. Japan, Canada, and several European countries have also established dedicated research centers focused on quantum networking. Within these laboratories, researchers are developing the technologies needed to distribute entanglement reliably. Single photon sources must generate entangled pairs with high precision. Optical fibers must transmit photons with minimal loss. Quantum memories are being developed to store entangled states temporarily, while network operations take place. Each of these components represents a complex scientific challenge. Quantum memories, for example, often rely on carefully prepared atomic systems that can absorb and later re-emit photons without destroying their quantum information. Maintaining the coherence of these stored states requires extremely controlled environments. Despite the difficulties, experimental demonstrations of small-scale quantum networks have already been achieved. Researchers have successfully distributed entangled photons between laboratories, separated by dozens or even hundreds of kilometers using optical fiber links. Other experiments have used free space transmission between mountaintop observatories or urban buildings. These early networks resemble the first experimental computer networks developed decades ago before the modern internet took shape. They are limited in scale but demonstrate the underlying principles needed for future expansion. One of the most important applications of these networks lies in secure communication. Quantum key distribution allows 2 distant parties to generate encryption keys that are guaranteed secure by the laws of quantum mechanics. If an eavesdropper attempts to intercept the quantum signals used to generate the key, the disturbance introduced by that measurement becomes visible in the data. Because entangled states can reveal violations of Bell inequalities, they provide particularly strong security guarantees. Future quantum networks could allow encryption keys to be distributed globally, with unprecedented levels of protection against interception. Beyond communication, quantum networks may also enable distributed quantum computing. In such systems, multiple quantum processors located in different laboratories could become linked through entangled connections. Instead of operating as isolated machines, these processors could cooperate, sharing quantum information across network links. This concept could eventually allow extremely large quantum computations to be performed by connecting many smaller processors together. Even more intriguingly, some researchers have suggested that quantum networks might serve as scientific instruments capable of probing fundamental physics. Entangled particles distributed across large distances could act as ultra-precise sensors, capable of detecting minute changes in gravitational fields or measuring subtle properties of spacetime itself. All of these possibilities rely on the same principle, first identified in the early debates about quantum mechanics. Particles that once interacted can remain connected through shared quantum states even after traveling far apart. By carefully creating and manipulating these connections, scientists are beginning to construct communication networks based not on classical signals alone, but on the deep correlations of quantum entanglement. The effort remains ongoing, and many technical obstacles still stand in the way. Yet the progress achieved so far suggests that the strange phenomenon once described as spooky by Albert Einstein may eventually form the backbone of entirely new global technologies, a network built not merely from cables and radio waves, but from the subtle connections woven through the quantum fabric of reality. For most of the history of physics, space and time were treated as the stage on which the universe performs its drama. Matter and energy moved through space. Events occurred in time. The geometry of space-time, described so beautifully by Albert Einstein's theory of general relativity, determined how gravity shaped the motion of planets, stars, and galaxies. Quantum mechanics, on the other hand, focused on the behavior of particles and fields at extremely small scales. For decades, these two great pillars of modern physics developed along largely separate paths. General relativity described the structure of space-time and gravity. Quantum mechanics explained atoms, radiation, and the microscopic world. Reconciling these two frameworks into a single consistent theory has proven one of the most challenging problems in theoretical physics. In recent years, however, an intriguing idea has begun to emerge. Some physicists now suspect that space-time itself may not be fundamental at all. Instead, the geometry of the universe might arise from deeper quantum relationships between underlying systems. And at the center of this possibility lies quantum entanglement. One of the most influential developments connecting these ideas came from theoretical physicist Juan Maldacena. In the late 1990s, Maldacena proposed a remarkable correspondence between two very different types of physical theories. This relationship is known as the anti-de Sitter conformal field theory correspondence, often described simply as the ADS-CFT correspondence. The proposal suggests that certain gravitational theories describing curved spacetime can be mathematically equivalent to quantum field theories defined on the boundary of that spacetime. In other words, a universe containing gravity can be fully described by a quantum theory that exists on a lower dimensional surface surrounding it. This idea connects closely with a concept known as the holographic principle. The holographic principle suggests that the information contained within a volume of space may actually be encoded on its boundary, much like a hologram stores a three-dimensional image on a two-dimensional surface. The principle emerged from earlier work by physicists such as Gerard 't Hooft and Leonard Susskind, while studying the physics of black holes. Black holes revealed a surprising property. The amount of information that can be stored within a region of space appears to scale with the area of its boundary rather than the volume inside it. Maldacena's work provided a concrete mathematical framework showing how such a relationship might operate in a fully consistent physical theory. Within the ADS-CFT correspondence, the gravitational geometry of the bulk spacetime is connected to the quantum entanglement structure of the boundary theory. This observation led to a remarkable line of thought. If the geometry of spacetime corresponds to patterns of entanglement within a quantum system, then perhaps spacetime itself emerges from those entanglement relationships. In this view, the fabric of the universe might be woven from networks of quantum correlations. Another provocative idea pushing this connection even further was proposed by Leonard Susskind together with Juan Maldacena. Their proposal became known as the ER=EPR conjecture. The name refers to two famous concepts in physics. The letters ER refer to Einstein-Rosen bridges, which are theoretical structures sometimes described as wormholes. These bridges arise from solutions of Einstein's equations of general relativity that connect two distant regions of spacetime through a tunnel-like geometry. The letters EPR refer to the Einstein-Podolsky-Rosen paradox, which introduced the strange correlations associated with quantum entanglement. Susskind and Maldacena suggested that these two ideas might be deeply connected. According to the ER=EPR conjecture, entangled particles may be linked by extremely tiny wormholes in the underlying geometry of spacetime. These wormholes would not allow travel or communication between the particles. They would be incredibly small and non-traversable structures, yet they could represent a geometric manifestation of quantum entanglement. If this idea is correct, entanglement would not simply describe correlations between distant particles. It would also reflect a hidden geometric connection within spacetime itself. Two entangled particles might, in some sense, be connected through the deeper architecture of the universe. Another important perspective on this possibility has been developed by theoretical physicist Mark van Ramsdonk. Van Ramsdonk explored how the geometry of spacetime might gradually emerge as quantum entanglement between parts of a system increases. His work considered simplified theoretical models in which a quantum field theory describing many interacting degrees of freedom could be divided into separate regions. When entanglement between those regions was reduced, the geometry of the corresponding spacetime began to fragment and disconnect. As entanglement increased, the geometry became more smoothly connected. This suggested a striking conclusion. The connectivity of spacetime itself might arise from patterns of quantum entanglement. If entanglement were removed entirely, spacetime could effectively fall apart into disconnected pieces. Although these ideas remain theoretical, they have inspired a rapidly growing area of research connecting quantum information theory with gravitational physics. Physicists now investigate how concepts such as entanglement entropy, quantum error correction, and information flow might help explain the structure of spacetime. For example, researchers studying the ADS-CFT correspondence have discovered that certain features of spacetime geometry can be reconstructed from entanglement patterns within the boundary quantum theory. These insights hint that geometry and information may be more closely related than previously imagined. Another intriguing connection arises from the mathematics of quantum error correction. In recent years, theorists have found that the structure of the holographic correspondence resembles the behavior of quantum error correcting codes used in quantum computing. These codes distribute information across many qubits, so that the original data can be recovered even if some qubits are lost or corrupted. Similarly, information about the interior of a gravitational spacetime appears to be encoded redundantly within the boundary quantum theory. This resemblance has led some physicists to suggest that spacetime itself may function like a quantum error correcting code. The geometry of the universe might represent a robust way of storing quantum information. These ideas are still evolving, and many questions remain unresolved. The ADS-CFT correspondence applies most directly to specific theoretical models of spacetime that differ from the expanding universe we observe. Extending these insights to realistic cosmology remains an active area of research. Nevertheless, the conceptual implications are profound. For centuries, space and time were regarded as the fundamental arena of physics. Matter and energy moved through spacetime, but spacetime itself was assumed to be a basic ingredient of reality. The study of entanglement suggests a different possibility. Perhaps spacetime is not fundamental after all. Perhaps the geometry of the universe arises from deeper quantum relationships between underlying systems. If that picture proves correct, the strange correlations that once puzzled Einstein may turn out to play a central role in shaping the very structure of reality. The invisible connections linking entangled particles might also be the threads from which the universe itself is woven. Black holes were once imagined as simple cosmic traps. Gravity becomes so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Matter falls inward, disappears from view, and the story appears to end there. For many years, this picture seemed complete. Then, during the 1970s, Stephen Hawking made a discovery that changed everything. While studying quantum field theory and the curved space-time around black holes, Hawking realized that black holes are not entirely black. Instead, they slowly emit radiation. This phenomenon, now known as Hawking radiation, arises from quantum processes near the event horizon. In quantum field theory, empty space is never truly empty. It constantly produces pairs of particles and antiparticles that briefly appear and then annihilate each other. Near the edge of a black hole, something unusual can happen to these pairs. If one particle falls into the black hole while its partner escapes into space, the escaping particle becomes real radiation. From a distant observer's perspective, the black hole appears to emit a faint stream of particles. Over extremely long timescales, this radiation gradually removes energy from the black hole. As a result, the black hole slowly shrinks and eventually evaporates. This insight revealed that black holes are not eternal objects. They have lifetimes, and over immense spans of time they disappear. Yet Hawking's calculation uncovered a deeper problem. The radiation emitted by a black hole appears to be completely random. It carries no information about the material that originally formed the black hole, or the matter that later fell inside it. This creates a paradox. Quantum mechanics contains a principle known as unitarity, which states that information about the state of a system cannot simply vanish. If a system evolves according to the laws of quantum mechanics, the information describing its initial conditions must remain encoded within its final state. But Hawking's calculation suggested that when a black hole evaporates, the information about everything that fell into it is lost forever. This conflict became known as the black hole information paradox. At the heart of the paradox lies quantum entanglement. The particles produced in Hawking radiation emerge as entangled pairs. One member of the pair escapes into space, while its partner falls into the black hole. Because the two particles are entangled, their quantum states remain linked. As more radiation escapes, the particles outside the black hole remain entangled with particles that have fallen inside the event horizon. Over time, a vast web of entanglement forms between the interior of the black hole and the radiation streaming away into space. If the black hole eventually disappears, the interior particles are gone. The radiation remaining in the universe would appear to be in a mixed random state, containing no information about what fell into the black hole. According to Hawking's original calculation, the information would be destroyed. Many physicists found this conclusion deeply troubling. Destroying information contradicts the fundamental principles of quantum mechanics. If black holes truly erased information, the entire framework of quantum theory might require revision. During the 1990s, physicist Don Page analyzed this problem in more detail. Page studied how the entanglement between Hawking radiation and the remaining black hole should evolve over time if information is ultimately preserved. His analysis led to a prediction now known as the Page curve. At first, the radiation emitted by a black hole should appear almost completely random, because it remains entangled with the interior of the black hole. As the black hole continues to evaporate, however, the pattern of entanglement must eventually change. After roughly half of the black hole's entropy has been emitted, the radiation should begin to carry increasing amounts of information about the interior. In this scenario, the later radiation would become correlated with the earlier radiation, gradually releasing the information that had previously been hidden behind the event horizon. If the Page curve is correct, the final state of all the radiation combined would still contain the information about everything that ever fell into the black hole. This proposal offered a possible path toward resolving the paradox, but it introduced new complications. The entanglement relationships required to preserve information appear to conflict with the entanglement structure predicted by Hawking's original calculation. In 2012, a group of physicists proposed a particularly striking version of this conflict. The researchers Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully examined the entanglement relationships involved in Hawking radiation and black hole evaporation. Their analysis led to a proposal now known as the firewall paradox. According to classical general relativity, an observer falling into a black hole should experience nothing unusual when crossing the event horizon. The horizon is not a physical surface. It is simply a boundary defined by the paths light can take. However, the firewall argument suggests that preserving quantum information might require a dramatic departure from this expectation. If the entanglement structure predicted by quantum information theory is correct, the smooth spacetime at the event horizon might break down. Instead of passing quietly into the black hole, an infalling observer might encounter an intense wall of high-energy particles. This hypothetical barrier became known as a firewall. The firewall proposal sparked intense debate among physicists. Many researchers found the idea unsettling because it seemed to violate the equivalence principle of general relativity. According to Einstein's theory, freely falling observers should not experience extreme conditions simply by crossing an event horizon. Resolving this tension has become one of the central challenges in modern theoretical physics. Over the past decade, new approaches combining quantum information theory with gravitational physics have begun to offer possible clues. One promising development involves the concept of quantum extremal surfaces and the so-called island formula. Researchers including Ahmed Al-Mahiri, Netta Engelhardt, Donald Marolf, and others have shown that certain calculations in gravitational systems reproduce the Page curve predicted by Don Page's earlier analysis. In these calculations, the information contained within Hawking radiation appears to be encoded in subtle ways involving regions of spacetime known as quantum islands. The mathematics suggest that information may not be lost after all. Instead, it may be encoded in complex entanglement structures linking the radiation and the geometry of spacetime itself. Although these ideas remain under active investigation, they illustrate how deeply entanglement lies at the heart of the paradox. The problem is not merely about black holes, it is about how quantum information behaves when gravity becomes extremely strong. Understanding that relationship may eventually lead to a deeper theory, unifying quantum mechanics with general relativity. Black holes, once considered simple gravitational traps, have therefore become powerful theoretical laboratories. They force physicists to confront the deepest questions about information, space-time, and the fundamental structure of the universe. And within those questions, entanglement appears again and again as a central thread. The same strange connections linking pairs of particles in laboratory experiments may also govern how information flows through some of the most extreme environments in the cosmos. In this sense, the study of black holes has transformed entanglement from a curious feature of quantum mechanics into a key ingredient in the search for a deeper understanding of reality itself. Quantum entanglement often appears in discussions about individual particles, photons travelling across laboratories, or delicate experiments testing the deepest foundations of physics. Yet one of the most fascinating places where entanglement naturally arises is not in empty space or isolated systems, but within ordinary materials. Inside solid matter, enormous numbers of quantum particles interact continuously. Atoms sit side by side in crystalline structures. Electrons move through metals and semiconductors. Magnetic moments align and fluctuate within complex lattices. At these microscopic scales, the behavior of matter is governed entirely by quantum mechanics. When many quantum particles interact strongly with one another, they form what physicists call a many-body system. In such systems, the state of each particle cannot be understood independently. Instead, the entire collection behaves as a deeply interconnected quantum object. Entanglement naturally emerges within these systems because the particles influence one another constantly. An electron moving through a metal, for example, does not behave like an isolated particle drifting freely through space. Its motion depends on interactions with surrounding electrons and atomic nuclei. These interactions generate collective quantum states in which large numbers of particles become correlated. The resulting behavior can be remarkably rich. Condensed matter physics, the branch of physics devoted to studying these systems, investigates how enormous collections of particles give rise to the everyday properties of materials. Electrical conductivity, magnetism, superconductivity, and many other familiar phenomena all emerge from complex quantum interactions. Within these materials, entanglement is not a rare occurrence, it is everywhere. One of the most intriguing aspects of these systems appears when materials undergo quantum phase transitions. In everyday life, phase transitions occur when matter changes from one state to another. Water freezing into ice or boiling into steam are familiar examples. These transitions are driven primarily by temperature. Quantum phase transitions are different. Instead of being triggered by thermal energy, they occur when changes in parameters such as pressure, magnetic field strength, or particle density alter the quantum ground state of a system. These transitions take place at temperatures extremely close to absolute zero, where thermal motion becomes negligible and quantum effects dominate. Physicist Subir Sachdev at Harvard University has been one of the leading researchers studying these phenomena. His work explores how interacting quantum systems reorganize themselves when the underlying parameters of a material change. At the critical point of a quantum phase transition, the correlations between particles can extend across enormous distances within the material. Electrons or spins separated by large regions of the lattice begin to behave as parts of a unified quantum state. The entire system becomes strongly entangled. Understanding these transitions requires tools capable of describing large-scale entanglement patterns. One of the most powerful concepts used in this area is entanglement entropy. As discussed earlier, entropy in physics measures the amount of uncertainty or information contained within a system. Entanglement entropy specifically quantifies how strongly different parts of a quantum system are correlated with one another. Imagine dividing a material into two regions. If the quantum states of the particles in those regions are completely independent, the entanglement entropy between them is minimal. But if the particles in one region are deeply correlated with particles in the other, the entanglement entropy becomes larger. By calculating how entanglement entropy behaves across different systems, physicists can gain insight into the structure of many-body quantum states. For example, many ordinary materials obey what is known as an area law for entanglement entropy. This means that the entanglement between two regions of a system grows roughly in proportion to the surface area separating them rather than the volume of the regions themselves. However, certain exotic quantum systems violate this pattern. Materials exhibiting unusual phases of matter, such as topological order, or strongly correlated electron states, can produce entanglement structures that behave in far more complex ways. Studying these patterns helps physicists identify new phases of matter that cannot be described using traditional concepts. Research in this area takes place in laboratories and theoretical institutes around the world. The Max Planck Institute for Quantum Optics in Germany has been a major center for experimental and theoretical work involving quantum many-body systems. Researchers there study ultra-cold atomic gases trapped within optical lattices created by intersecting laser beams. These systems allow physicists to simulate the behavior of complex materials using carefully controlled quantum particles. Atoms cooled to temperatures extremely close to absolute zero can occupy lattice sites arranged in regular patterns. By adjusting the intensity and geometry of the laser beams, scientists can control how strongly the atoms interact with one another. This makes it possible to create artificial quantum materials where entanglement and correlations can be studied directly. Meanwhile, the Kavli Institute for Theoretical Physics in California has served as a hub for collaborative research on condensed matter theory. Physicists working there explore mathematical models describing interacting quantum systems, often uncovering new insights into how entanglement organizes itself within complex materials. Condensed matter experiments provide something extremely valuable to physicists interested in entanglement. They offer real controllable systems in which complex quantum correlations naturally arise, while theoretical discussions about entanglement often involve isolated particles or abstract models. Condensed matter systems contain trillions of interacting particles whose collective behavior can be observed directly. These systems act as laboratories for studying how entanglement spreads, evolves, and shapes the properties of matter. One striking example appears in superconductivity. In superconducting materials, electrons form correlated pairs known as Cooper pairs. These pairs move through the material without electrical resistance, producing currents that can flow indefinitely. The formation of Cooper pairs involves entanglement between electrons with opposite momenta and spin orientations. This entanglement allows the electrons to behave collectively rather than as independent particles. Similarly, in certain magnetic materials, spins within the lattice become entangled in patterns that produce exotic quantum phases. Researchers have discovered materials known as quantum spin liquids, in which magnetic moments never settle into a fixed arrangement even at extremely low temperatures. Instead, they remain in fluctuating entangled states that extend across the entire material. These systems are particularly fascinating because they reveal how entanglement can stabilize entirely new forms of matter. In recent years, condensed matter experiments have also begun exploring connections between entanglement and other areas of physics. Techniques developed in quantum information theory are now used to analyze the entanglement structure of many body systems. At the same time, condensed matter models have inspired ideas about quantum gravity, holography, and the emergence of spacetime geometry. The boundaries between fields that once seemed separate have begun to blur. A crystal lattice filled with interacting electrons may appear very different from the curved spacetime around a black hole. Yet both systems exhibit patterns of quantum entanglement that shape their behavior. By studying materials in laboratories here on Earth, physicists are gaining insight into some of the deepest principles governing the universe. What once seemed like a subtle feature of quantum mechanics has turned out to be a powerful organizing principle underlying the behavior of matter itself. Entanglement is not confined to isolated particles in carefully prepared experiments. It quietly weaves through the microscopic structure of materials all around us, shaping the collective behavior of the quantum world in ways that continue to surprise and inspire scientific discovery. Quantum entanglement is not merely a technical concept used in laboratories and experiments. It also sits at the heart of one of the deepest philosophical questions in physics. What does quantum mechanics actually mean? The mathematical framework of quantum theory is extraordinarily successful. Its predictions match experimental observations with astonishing precision. Yet the equations themselves do not always explain what is really happening beneath the surface. Physicists can calculate the probability of measurement outcomes, predict interference patterns, and design experiments involving entangled particles. But the deeper interpretation of these results remains open to debate. Over the past century, several different interpretations of quantum mechanics have been proposed in an attempt to explain what the theory is truly describing. Each interpretation accepts the same mathematical structure and experimental predictions. The difference lies in how those results are understood. One of the earliest and most widely discussed alternatives emerged in the 1950s through the work of the American physicist Hugh Everett. Everett proposed what is now known as the many-worlds interpretation of quantum mechanics. In the conventional Copenhagen interpretation, the wave function describing a quantum system evolves smoothly until a measurement occurs. At that moment, the wave function appears to collapse into a single definite outcome. Everett questioned whether this collapse process was really necessary. Instead of assuming that the wave function suddenly chooses one outcome, Everett suggested that all possible outcomes continue to exist simultaneously. When a measurement occurs, the universe effectively branches into multiple versions, each corresponding to a different result. In this picture, the wave function never collapses at all. Instead, reality continually splits into a vast collection of parallel branches, representing every possible outcome of quantum events. Entanglement plays a central role in this interpretation. When two particles become entangled, their combined quantum state describes all possible measurement outcomes simultaneously. According to Everett's proposal, when observers measure those particles, the observers themselves become entangled with the results. Each branch of the universe contains a consistent history in which a particular outcome occurred. From the perspective of any observer inside one branch, the other branches remain inaccessible. The many-worlds interpretation therefore removes the need for wave function collapse entirely. The apparent randomness of quantum measurements arises because observers find themselves within only one branch of a much larger quantum reality. Some physicists find this interpretation appealing because it treats the wave function as a real physical object that evolves according to a single, consistent equation. Others remain uneasy with the idea that the universe might continually split into countless parallel histories. Another interpretation takes a very different approach. In the 1950s, physicist David Bohm revived an earlier concept first explored by Louis de Broglie. This approach is often called pilot wave theory, or Bohmian mechanics. In Bohm's model, particles always possess definite positions and trajectories. Unlike the Copenhagen interpretation, which treats particle properties as undefined until measured, Bohmian mechanics assumes that particles follow precise paths at all times. However, their motion is guided by a wave function that evolves according to the usual equations of quantum mechanics. This wave function acts as a guiding field influencing how particles move through space. In Bohm's interpretation, entanglement arises because the guiding wave function describes multiple particles as part of a single unified system. The motion of one particle can depend on the positions of other particles through this shared guiding field. The result is a form of non-local behavior. Changes affecting one part of an entangled system can influence the motion of distant particles because the guiding wave function connects them. Importantly, Bohmian mechanics reproduces the same experimental predictions as standard quantum theory, yet it offers a different picture of reality. Instead of probabilities and wave function collapse, Bohm's interpretation describes particles moving along definite paths guided by an underlying quantum field. Some physicists appreciate this interpretation because it restores a sense of determinism to quantum mechanics. Others note that the theory introduces non-local influences that appear difficult to reconcile with relativity. Still another perspective emerged during the 1990s through the work of Italian physicist Carlo Rovelli. Rovelli developed an approach known as relational quantum mechanics. This interpretation begins with a simple but radical idea. Physical properties do not exist in an absolute sense. Instead, properties only exist relative to other systems. In everyday language, objects appear to possess definite characteristics regardless of who observes them. A table has a position, a mass, and a shape, whether or not anyone is looking at it. Quantum mechanics, however, suggests that the situation may be more subtle. In relational quantum mechanics, the state of a system is always defined relative to another system performing a measurement or interaction. There is no single universal description of reality that applies independently of all observers. Instead, reality consists of a network of relationships between interacting systems. Entanglement fits naturally into this framework. When two particles become entangled, their properties are defined only in relation to one another. Measurements performed on one system establish correlations that are meaningful only within the context of the interaction between observer and observed. According to this interpretation, quantum mechanics does not describe absolute properties of isolated objects. It describes how systems relate to one another through interactions. Different observers may legitimately assign different quantum states to the same system depending on the information available to them. Although these interpretations differ dramatically in their philosophical implications, they all reproduce the same experimental predictions. Whether one imagines branching universes, guiding pilot waves, or relational networks of interactions, the mathematical results remain identical. Entangled particles still exhibit the same correlations. Bell inequalities are still violated. Quantum teleportation and quantum computing still operate according to the same underlying equations. This situation highlights one of the most fascinating aspects of modern physics. The theory works extraordinarily well, yet its deeper meaning remains open to interpretation. Entanglement lies at the center of this mystery. It reveals that particles can share connections that transcend classical ideas about independence and locality. Yet the precise nature of those connections depends on how one chooses to interpret the theory itself. Some physicists prefer interpretations that maintain deterministic laws beneath the probabilistic surface. Others embrace the possibility that reality may branch into multiple histories, or that physical properties emerge only through relationships between systems. For now, experiments continue to confirm the predictions of quantum mechanics without settling the question of interpretation. The equations remain clear, the experiments remain reliable. But the deeper story behind entanglement, and what it ultimately reveals about the nature of reality, remains one of the most intriguing puzzles in all of science. For most of human history, the universe seemed to follow a simple rule. Objects were separate. A stone lying on the ground did not influence another stone across the valley. A planet orbiting a distant star did not affect events on Earth. The world appeared to consist of individual pieces, each interacting locally with its immediate surroundings. Classical physics reinforced this picture. Isaac Newton described gravity as a force acting between masses across space. Later, James Clerk Maxwell showed that electric and magnetic fields spread through space in waves travelling at finite speeds. Even when forces acted at a distance, they did so through well-defined mechanisms moving through space. The assumption underlying all of these ideas was locality. Events occurring here should not instantly affect events happening somewhere far away. Quantum entanglement quietly challenged this assumption. At first, the challenge appeared small. Early quantum physicists discovered that when particles interact and then separate, their mathematical description sometimes cannot be divided into independent pieces. The wave function describing the system must treat both particles together as a single entity. This strange feature puzzled many of the scientists who helped build quantum theory. Albert Einstein, in particular, found the idea deeply unsettling. Along with Boris Podolsky and Nathan Rosen, he developed the famous Einstein-Podolsky-Rosen argument during the 1930s. Their thought experiment suggested that quantum mechanics might be incomplete. Einstein suspected that hidden variables might exist beneath the surface of quantum theory. These variables could secretly determine the outcomes of measurements while preserving the principle of locality. He famously referred to entanglement as spooky action at a distance, a phrase that captured his discomfort with the idea that distant particles might share immediate correlations. For several decades, the debate remained unresolved. Quantum mechanics worked extraordinarily well as a predictive tool, yet many physicists wondered whether a deeper theory might eventually restore a more classical understanding of reality. The turning point arrived when John Bell derived a set of inequalities during the 1960s. Bell demonstrated that any theory based on local hidden variables must obey specific limits on the correlations between distant measurements. Quantum mechanics predicted violations of those limits. Suddenly, the debate moved from philosophy to experiment. If the inequalities were violated, then nature itself would reject the classical assumptions of locality, combined with hidden variables. Beginning in the 1970s, experimental physicists began performing increasingly precise tests, using entangled photons and other quantum systems. Researchers such as John Clauser, Stuart Friedman, and later Alain Aspect carried out experiments measuring the polarization correlations between entangled particles. Again and again, the results confirmed the predictions of quantum mechanics. Bell inequalities were violated. The universe behaved in a way that no local hidden variable theory could reproduce. Over time, improvements in experimental technology strengthened these conclusions. More advanced photon detectors, fast-switching measurement devices, and increasingly sophisticated experimental designs eliminated potential loopholes that critics once raised. Today, the experimental evidence supporting entanglement is overwhelming. Particles that share a common quantum state can exhibit correlations that cannot be explained by any classical mechanism confined to local interactions. Importantly, these correlations do not allow faster-than-light communication. The statistical patterns only become visible when measurement results are compared through ordinary communication channels. Relativity remains intact. Yet the existence of these correlations forces physicists to rethink the classical idea that distant objects always behave independently. The implications reach far beyond philosophical debates. Entanglement has become a central resource in modern technology. Quantum cryptography uses entangled particles to generate encryption keys whose security is guaranteed by the laws of physics rather than by mathematical complexity alone. Any attempt to intercept the quantum signals leaves detectable traces within the correlations. Quantum teleportation uses entanglement to transfer quantum states between distant systems without physically sending the particles themselves. Quantum computing relies on entangled qubits to perform calculations that would be extraordinarily difficult for classical machines to simulate. Research laboratories around the world are building quantum processors capable of manipulating entangled states among dozens or even hundreds of qubits. These machines remain experimental, but steady progress continues. At the same time, physicists are developing quantum communication networks designed to distribute entangled particles across continents and even through satellites orbiting Earth. What once appeared as a curious mathematical feature of quantum equations has evolved into a powerful tool for processing information. Yet beyond these practical applications, entanglement continues to raise deeper questions about the nature of reality. Some theoretical physicists now suspect that entanglement may play a role in the very structure of spacetime. Research involving the holographic principle, the ideas CFT correspondence developed by Juan Maldacena, and ideas explored by Leonard Susskind and Mark van Raamsdonk suggest that the geometry of spacetime might emerge from patterns of quantum correlations. In these theoretical frameworks, the connectivity of space could arise from networks of entangled quantum states. If entanglement were somehow removed, spacetime itself might fragment into disconnected regions. Although these ideas remain speculative, they illustrate how far the concept of entanglement has expanded since its introduction, nearly a century ago. What began as a puzzling feature of quantum theory has become a bridge connecting multiple areas of physics, from laboratory experiments involving single photons to theoretical investigations of black holes and spacetime geometry. Entanglement appears repeatedly as a fundamental thread. The idea also invites a subtle shift in perspective. Instead of viewing the universe as a collection of isolated objects interacting occasionally across space, entanglement suggests a deeper level of connectedness. Particles that once interacted may continue to share aspects of a unified quantum description even after traveling enormous distances apart. Their behavior cannot always be understood independently. The universe, in this sense, may be less like a set of separate pieces and more like a vast network of relationships. Each interaction leaves traces within the quantum structure of the system, linking particles together in ways that persist across space and time. This does not mean that everything in the universe is directly entangled with everything else. Interactions with the environment gradually reduce and redistribute entanglement in complex ways. Yet the principle itself reveals that the fundamental laws of nature allow connections far richer than classical intuition once imagined. Einstein hoped that a deeper theory might restore a more familiar picture of reality. Instead, the decades of research that followed revealed something even more intriguing. The universe truly does permit distant systems to share correlations that cannot be explained by classical physics alone. What once appeared spooky has become one of the most carefully tested features of modern science. And perhaps, at the deepest level, entanglement hints at a profound truth. Reality itself may not be built from isolated parts. It may instead be woven together through an intricate network of quantum relationships, connecting the smallest particles with the largest structures of the cosmos in ways that physics is only beginning to understand. Across the past century, the idea of quantum entanglement has gradually reshaped how physicists think about reality. What first appeared as a peculiar mathematical feature of quantum equations has grown into one of the most revealing insights about the structure of nature. In the early years of quantum mechanics, entanglement was largely seen as a curiosity. The theory describing atoms and particles produced extremely accurate predictions, yet some of its implications seemed difficult to accept. Particles that had once interacted could later behave as parts of a single shared system, even after travelling vast distances apart. To many physicists trained in classical thinking, this idea seemed deeply unsettling. Albert Einstein famously resisted the notion that distant systems might exhibit such correlations. Along with Boris Podolsky and Nathan Rosen, he argued that quantum mechanics might be incomplete, suggesting that hidden variables could restore a more intuitive description of physical reality. Erwin Schrodinger, who helped formulate the mathematics of wave mechanics, was the physicist who first gave this strange connection its name. He called it entanglement. Schrodinger recognized that entanglement represented something fundamentally new in physics. Classical systems could always be described by listing the properties of their individual parts. Quantum systems, however, sometimes refuse to be separated in this way. Their description belonged to the system as a whole. For decades, the meaning of this idea remained uncertain. The equations of quantum theory worked perfectly in laboratories, yet many scientists wondered whether a deeper explanation might eventually restore a more familiar picture of independent particles interacting locally. The debate shifted dramatically in the 1960s, when the physicist John Bell derived a set of mathematical inequalities that allowed these philosophical questions to be tested experimentally. Bell showed that if hidden variables existed and obeyed the principle of locality, then certain limits would appear in the correlations between measurements performed on distant particles. Quantum mechanics predicted that these limits could be exceeded. Experiments performed during the following decades gradually confirmed Bell's prediction. Researchers such as John Clauser, Alain Aspect, and Anton Zeilinger conducted increasingly refined tests using entangled photons and other quantum systems. The results repeatedly violated Bell inequalities. Nature itself appeared to favor the predictions of quantum mechanics. These experiments did not allow faster-than-light communication or violations of relativity, but they demonstrated that quantum correlations could not be explained through classical local mechanisms. Entanglement was real. As experimental techniques improved, entanglement transformed from a philosophical puzzle into a powerful scientific resource. Quantum information theory emerged as a new field exploring how entangled systems can process and transmit information in ways impossible for classical devices. Quantum computing uses entangled quantum bits, often called qubits, to explore computational possibilities that extend beyond traditional binary machines. Certain quantum algorithms promise dramatic speed advantages for particular types of problems, including tasks involving number factoring and database searching. Quantum cryptography applies entanglement to secure communication systems. By distributing entangled particles between distant locations, encryption keys can be generated in ways that reveal any attempt at interception. Entanglement has also enabled the development of quantum teleportation protocols that transfer quantum states between distant systems. These technological applications represent only one side of the story. At the same time, theoretical physics has increasingly recognized that entanglement may illuminate deeper aspects of the universe. In condensed matter physics, entanglement helps scientists understand complex materials whose behavior cannot be described through independent particles alone. In quantum gravity research, some theorists suspect that the geometry of spacetime itself may emerge from patterns of quantum entanglement. Ideas such as the holographic principle and the ADS-CFT correspondence suggest that information and correlations among quantum systems may play a role in shaping the structure of space. Some theoretical proposals even explore the possibility that spacetime connectivity might arise from networks of entangled quantum states. Although these ideas remain under active investigation, they illustrate how widely the concept of entanglement now reaches across modern physics. From the smallest particles to the largest structures of the cosmos, entanglement appears again and again as a central theme. It bridges disciplines that once seemed separate. Quantum information theory, particle physics, condensed matter research, and cosmology now share common mathematical tools for describing entangled systems. This unity hints that entanglement may reflect a deeper organizing principle within nature itself. The implications extend beyond physics laboratories and research papers. Entanglement gently challenges the everyday intuition that objects exist as completely independent entities. At the most fundamental level, the universe may be less like a collection of isolated pieces and more like a vast web of relationships. Interactions between particles can leave traces that persist long after those particles separate. Quantum systems can retain subtle connections woven into their shared wave functions, linking distant regions of space through patterns of correlation. Most of the time, these connections remain hidden beneath the familiar behavior of the classical world. Interactions with the surrounding environment quickly spread and redistribute quantum correlations, making them difficult to observe directly in everyday objects. Yet careful experiments continue to reveal that these connections exist. And each new discovery adds another layer to the evolving understanding of how the universe operates. From Einstein's skepticism to the experimental breakthroughs of the late 20th and early 21st centuries, the study of entanglement has become one of the most remarkable scientific journeys of modern times. It has forced physicists to reconsider assumptions about locality, separateness, and the nature of information. Perhaps most importantly, it has revealed that the universe contains forms of connection far richer than classical intuition once suggested. Quantum entanglement does not simply describe an unusual property of particles. It reveals something deeper about how reality itself may be organized. Beneath the familiar world of objects and distances, there may exist a subtle network of relationships linking physical systems together in ways that are only beginning to be understood. For now, entanglement remains one of the most profound discoveries in modern science, and as research continues, it may yet reveal even deeper layers of connection hidden within the fabric of the universe.